During one of the strangest chapters in Earth's history, ice crept from the poles almost to the equator, turning the planet into a near-global snowball and pushing life to the edge of survival. In this video, we quietly explore how it happened, how life endured, and how Earth thawed. If you enjoy calm journeys through deep time, please like, subscribe, and share. In a quiet corner of a spiral galaxy, a small yellow star circles the center in a broad, nearly flat orbit, taking hundreds of millions of years to complete a single path. Around this star, a family of planets moves in nearly regular tracks, and among them is one world that sits within a range where liquid water can persist on its surface for long stretches of time. This is Earth, a rocky planet that forms about 4.5 billion years ago from dust gas and collisions between countless small bodies. In the early solar system, space near the young sun is crowded with fragments of rock and ice. They follow intersecting paths, collide, merge, and sometimes shatter. The energy released in each impact melts. Rock evaporates volatile elements and briefly turns parts of the growing planet into oceans of magma. Over time, the impacts become less frequent and a more stable world begins to emerge. In one very large collision, a body roughly the size of Mars strikes the young Earth. Most of the visible evidence of this event is erased by later processes at the surface, but its legacy remains overhead. Material thrown into orbit coalesces to form the Moon. The Earth-Moon system settles into a long partnership that influences ocean tides, the length of the day, and the steadying of Earth's axial tilt. The planet slowly cools from its early molten state, and a solid crust forms over a still hot interior. Heat continues to leak out from the inside through convection in the mantle and through volcanic activity. This internal heat drives plate tectonics, the slow movement of rigid plates of crust over the softer layer beneath. The plates carry the continents and ocean basins across the face of the planet at rates of only a few centimeters per year, but over tens and hundreds of millions of years these movements rearrange the entire surface. While the solid Earth evolves, the star at the center of the system also changes. In its youth, the sun is fainter than it is today. Its energy output slowly rises over billions of years as hydrogen is fused into helium in its core. Early in Earth's history, the sun shines with less power, yet the planet is not permanently frozen. Greenhouse gases in the atmosphere trap heat, compensating for the lower brightness. This balance between the energy received from the sun and the way the planet stores and releases that energy shapes climate over deep time. The Earth orbits at a distance where the average incoming sunlight is neither overwhelmingly strong nor too weak. If the planet were much closer to the sun, water at the surface could be lost more rapidly to space, and if it were much farther away, permanent global ice could be more likely. Within this broad habitable zone, many factors adjust the details of climate, but the basic setting is that of a world that can sustain liquid water at its surface for long periods. Over billions of years, the length of the day gradually increases as the tidal interaction with the Moon transfers angular momentum and slows Earth's rotation. The continents move in slow arcs, sometimes gathering into large supercontinents, sometimes breaking apart into smaller landmasses. Ocean basins open and close. Mountain ranges rise and then wear down under weather and erosion. Above, the atmosphere changes in composition with gases added by volcanoes removed by chemical reactions, with rocks, and influenced by living organisms once life becomes established. To follow the timing of these changes, it is helpful to compress Earth's history into a single notional day. At midnight, the planet forms from the debris of the solar system. Not long after, the giant impact that produces the Moon takes place, and the surface remains extremely hot. By the early hours of this imagined day, the crust has cooled enough for a solid surface, and for water to collect in basins as oceans. By around 4 in the morning on this scale, the first simple life appears likely in the form of single-celled organisms that draw energy from chemical reactions or from sunlight. For many hours of this compressed day, life remains microscopic. Bacteria and other simple cells colonize the oceans, interact with minerals, and slowly alter the composition of the atmosphere by processes such as photosynthesis, which produces oxygen as a byproduct. As the day progresses toward noon and beyond, continents are surrounded by shallow seas and microbial communities spread across a variety of environments. At this stage, there are still no plants or animals on land. The surface remains the domain of bare rock water and networks of tiny organisms. Through the afternoon and early evening of this symbolic day, the interplay between solar energy, internal heat, plate tectonics, and the evolving atmosphere continues to shape climate. The sun grows slightly brighter, but changes in greenhouse gases and in the arrangement of continents adjust how much heat the planet retains. At times, ice sheets grow at high latitudes and then retreat. At other times, warmer periods prevail. Earth experiences several ice ages even before the extreme events that will later be known as Snowball Earth. But these earlier glaciations do not reach all the way to the equator. The overall pattern is one of gradual change, punctuated by episodes of cooling and warming, all unfolding over spans of time that are hard to grasp in human terms. Near the late evening hours on this compressed clock, roughly between 8 and 9 at night, a particular interval of Earth history begins. Scientists call this era the Neoproterozoic, which means new earlier life. It spans from about 1 billion years ago to around 540 million years ago. During this interval, the continents have gathered into and broken apart from supercontinents, and chemical conditions in the oceans and atmosphere are shifting. The balance between incoming sunlight, greenhouse gases, and reflective surfaces is moving toward a state in which ice can gain an unusual advantage. The sun by this time is somewhat brighter than it was in the distant past, but other factors start to favour cooling in a way that is different from previous episodes. The stage is gradually set for glaciations of unusual reach and strength events in which ice will eventually advance far beyond its usual high-latitude domains. In this outer view, the planet remains a small sphere of rock and water, orbiting a stable star subject to slow but steady changes in energy from above and heat from below. Over hundreds of millions of years, these quiet processes bring Earth toward a critical period when the balance of its climate system will tip and global glaciations will transform the surface in ways that later observers piece together from the clues left in rocks and in the record of deep time. As Earth continues its slow path around the Sun, its orbit is not a fixed and perfect circle. Over very long spans of time, the shape of the orbit, the angle of the planet's spin axis, and the direction that axis points all change in regular patterns. These are often called orbital cycles. They act like quiet background controls on climate, adjusting how sunlight is distributed over the planet's surface from season to season and from age to age. The first of these cycles concerns the shape of Earth's orbit, a property known as eccentricity. At some times, the path is almost a perfect circle, so the distance between Earth and the Sun changes very little over the course of a year. At other times, the orbit becomes slightly more stretched, closer to an ellipse, so that there is a more noticeable difference between the closest and farthest points from the Sun. The changes in eccentricity unfold over cycles that last on the order of 100,000 years and longer. The shift in total sunlight from this alone is modest, but it alters how the seasons respond to other changes, and it can help start or end ice ages when combined with other factors. A second important cycle involves the tilt of Earth's axis known as obliquity. The axis is not upright with respect to the plane of the orbit but inclined. Today it is tilted by a little more than 23 degrees. This tilt is what gives the planet its seasons as each hemisphere leans toward or away from the sun in turn. Over a cycle of about 41,000 years, the tilt slowly increases and then decreases by a few degrees. When the tilt is greater, the contrast between seasons becomes stronger. Summers are warmer and winters colder, especially at higher latitudes. When the tilt is smaller, seasons become milder with cooler summers and less severe winters. The amount of sunlight received during summer at high latitudes is a key factor in whether large ice sheets grow or shrink. A third cycle involves the slow wobble of the spin axis itself, known as precession. This wobble is partly caused by the gravitational pull of the Moon and the Sun on the slightly flattened Earth. Over a period of roughly 20,000 years, the axis traces a circle in space like a very slow spinning top. Because of this, the timing of the seasons shifts relative to Earth's position along its orbit. In one phase of the cycle, the northern hemisphere has summer when Earth is closer to the Sun, and in another phase, northern summer occurs when Earth is farther away. This does not change the total amount of sunlight over a year, but it does change how that energy is distributed among the seasons and between hemispheres. When eccentricity, tilt, and precession line up in certain ways, they can favour the growth of large ice sheets on continents at high latitudes. When summer sunlight there becomes weak enough, winter snow does not melt completely. Layers of snow build up year after year, compress into ice and form glaciers that can slowly spread. When the combinations are different, stronger summer sunlight melts more snow and ice, and glaciers retreat. These cycles are not strong enough on their own to control every detail of climate, but they set a rhythm that can be seen in many past ice ages over the last few million years. The orbital cycles operate like a long, slow pattern of beats. They do not create the drums, but they influence when the drums are more likely to sound. Over intervals of tens of millions of years, the arrangement of the continents on the surface also plays a role that dovetails with these orbital changes. Because tectonic plates drift, land masses move toward or away from the poles. When large continents sit near the poles, snow that falls on them in winter has a better chance of surviving the summer, so ice sheets can grow more easily. When most land is near the equator, high-latitude oceans can remain relatively free of permanent ice, because open water releases heat and helps keep nearby regions milder. The presence or absence of broad ice-friendly continents near the poles therefore modulates the effect of orbital changes. At certain times in Earth history, mountains rise in belts that run roughly east to west, at high or mid-latitudes. Their high elevations and colder temperatures make them natural sites for snow accumulation. The erosion of these mountains and the way they interact with wind and moisture patterns further adjust the background conditions under which ice sheets advance or retreat. Over hundreds of millions of years, the slow rearrangement of continents, mountain chains, and ocean basins shifts the basic climate pattern on which shorter orbital cycles ride. Far above all of this, the sun continues to brighten at its own slow pace. Over the span of 1 billion years, its energy output increases by a noticeable fraction, but over the shorter intervals of orbital cycles and plate drift, this brightening is almost constant. On those shorter scales, the key changes are not the total power of the sun, but how Earth's geometry, spin, and surface arrangement decide where and when that power arrives. In the last few million years, evidence from ocean sediments and ice cores shows that ice ages have come and gone roughly every 100,000 years, closely matching the period of one of the eccentricity cycles. Smaller variations with periods of about 41,000 and about 20,000 years appear in the record as well, reflecting tilt and precession. These data come from layers of mud on the seafloor, tiny shells of microorganisms and bubbles of ancient air trapped in ice. They show that orbital cycles are written into the recent climate history of the planet. In the more distant past, the direct evidence becomes less detailed, but the same physical principles apply. At times, orbital conditions favour cooler climates and more extensive ice. At other times, they favour warmer climates and reduced ice. Meanwhile, long-term changes in greenhouse gas levels, volcanic activity and rock weathering gradually shift the baseline temperature around which these orbital rhythms cause smaller swings. There are intervals when orbital conditions alone can trigger relatively modest ice ages and interglacials, and there are other intervals when the same orbital nudges act on a climate system that is already moving toward a more extreme state. During the Neoproterozoic, the position of continents and the slow evolution of the atmosphere create a different background from the one that exists in more recent times. Large land masses lie in low latitudes rather than clustered around the poles. The long arcs of plate motion are bringing together and pulling apart supercontinents in ways that change ocean circulation and the distribution of rainfall. These tectonic changes, combined with the quiet, predictable variations in Earth's orbit and axis, shape how sunlight is stored or reflected over the globe. In some configurations, ice remains mostly confined to polar regions. In others, given the right conditions, the same cycles can help ice grow more widely. Through all of this, Earth stays bound to the Sun by gravity turning once each day, orbiting once each year, and shifting its orientation in patterns that repeat over tens and hundreds of thousands of years. These regular motions do not act suddenly. They work over spans of time longer than human history, longer even than the lifetimes of many species. Yet they form part of the slow background that guides when ice can advance, when it can retreat, and when the climate system approaches thresholds beyond which it can behave in ways that are less familiar when compared with the more recent ice ages, whose traces are easier to study. In this way, the drifting orbits, the changing tilt, the slow wobble of the axis, and the journeys of continents all contribute to a long and gentle shaping of climate-preparing conditions, under which at certain times glaciations of unusual reach can become possible on a small rocky planet circling its star. In the hundreds of millions of years before the great Neoproterozoic glaciations, Earth's climate sits in a range that can be described as moderate when compared with the extremes that will follow. The sun is somewhat dimmer than today, but not by a large margin, and greenhouse gases in the atmosphere help maintain surface temperatures that allow liquid water across wide areas of the globe. Shallow seas flood the edges of continents. Waves and tides move over long, low coastlines. Above clouds form and dissipate as water evaporates from warm ocean surfaces and returns as rain or snow. On long timescales, this climate is not static. It fluctuates around a shifting baseline that is set by volcanic outgassing, the breakdown of rocks at the surface, and the slow motions of continents that control where land and sea are placed. In the oceans, simple life is already present. Microbial communities cover sediments and hard surfaces, forming films and layered structures. Some of these microbes use sunlight to drive photosynthesis, splitting water and releasing oxygen. Others rely on chemical reactions involving dissolved minerals. Together they contribute to a slowly changing balance of gases in the atmosphere and oceans. Oxygen levels in the air remain far below those of the modern world, yet they are higher than in earlier eras and continue to rise in small steps. Carbon dioxide and other greenhouse gases, meanwhile, are added to the atmosphere by volcanoes that release gases from the interior. At the same time, they are removed by processes at the surface. One of the most important of these is chemical weathering. When carbon dioxide in the air dissolves into tiny droplets of water, it forms a weak acid. This slightly acidic water falls as rain onto exposed rocks. Over time, it reacts with minerals in the rock, breaking them down and forming dissolved substances that are carried by rivers to the sea. In the oceans, some of these dissolved components eventually become part of carbonate minerals, which settle to the seafloor and are buried in sediments. In this way, carbon that once resided in the atmosphere as carbon dioxide becomes locked into solid rock. The rate of this weathering depends on temperature, rainfall, and the position of continents. Warm, wet conditions promote faster reactions. When large areas of land lie in the tropics where solar heating and rainfall are both high, the removal of carbon dioxide through weathering can be especially efficient. In the lead-up to the Snowball Earth events, plate motions bring many of Earth's continents into low latitudes. Land that once lay close to the poles moves toward the equator and joins into large assemblies sometimes described as supercontinents. These landmasses experience intense sunlight and frequent heavy rainfall. Rivers cut into their surfaces and carry weathered material toward surrounding seas. The high rate of chemical breakdown of rocks under these conditions tends to lower atmospheric carbon dioxide over long spans of time. Volcanic outgassing continues to supply new carbon dioxide from the mantle, but in some intervals the balance between addition and removal slowly shifts. If weathering outpaces outgassing for long enough, greenhouse gas levels in the atmosphere can decline. As greenhouse gases fall, the ability of the atmosphere to retain heat from the sun weakens and global temperatures drift downward. This is not a sudden shift, but a gradual cooling that unfolds over millions of years. Ice at high latitudes becomes more persistent. Snow that falls on polar continents melts less completely each summer. Glaciers that already exist on high mountains extend a little farther down valleys, and small ice caps grow on uplands that were previously seasonally snow-covered. In this period, however, Earth still resembles a familiar water world rather than an ice-covered sphere. Open oceans stretch from low to mid-latitudes, absorbing sunlight and releasing heat back into the air. The contrast between tropical warmth and polar cold supports atmospheric circulation cells that move heat and moisture around the globe. Winds carry moist air toward mountain ranges where it rises, cools, and drops snow. Storm tracks sweep across mid-latitudes. Local and regional climates differ, but the general pattern remains one where liquid water is widespread, and large parts of the surface remain ice-free. The distribution of continents and ocean basins influences the paths of ocean currents. Where seaways connect low and high latitudes, warm water can flow poleward near the surface, bringing heat from the tropics toward colder regions. In turn, cold, dense water can sink and return toward the equator at depth. These currents act as a conveyor of heat and dissolve substances, smoothing out temperature differences and supplying nutrients to marine life. Changes in the shapes of ocean basins, the depth of seaways, and the positions of continental barriers slowly reshape this circulation, altering how effectively heat is transported. During the late Neoproterozoic, some reconstructions suggest that large land masses near the equator interrupt certain ocean pathways, affecting how warm water can move toward high latitudes. This can favor cooler conditions in polar regions and make it easier for ice to grow there. As climate cools, the brightness or albedo of some regions increases. Snow and ice reflect a higher fraction of incoming sunlight back to space than bare rock or open water. As snowy and icy surfaces expand in area, they cause local cooling to become slightly stronger because less solar energy is absorbed. At first, this effect is modest and remains limited to high latitudes and high elevations. Over time, as more land and sea surfaces become seasonally snow-covered or ice-covered, the albedo effect grows. In most climate states, this remains a stabilizing influence that does not run away. As temperatures fall, weathering of rocks can slow down in some regions, because cold conditions reduce rainfall and limit the rate of chemical reactions. When weathering slows, less carbon dioxide is removed from the atmosphere, and volcanic outgassing can then rebuild greenhouse gas levels, pushing temperatures back upward. This feedback tends to keep the planet from drifting too far into extreme cold. In the long interval before Snowball Earth, this balance between cooling and warming processes is maintained, though it may become more delicate as land remains concentrated in the low latitudes. Meanwhile, life in the oceans contributes its own small but persistent influence. Photosynthetic microbes in the surface layers of the sea take in carbon dioxide dissolved in water, use its carbon to build organic matter and release oxygen. Some of this organic matter sinks into deeper waters and into sediments, transferring carbon from the surface system into long-term storage. Microbial communities also build carbonate structures such as layered mounds and reefs that incorporate carbon into solid minerals. These processes, acting over tens and hundreds of millions of years, can alter atmospheric and oceanic carbon levels. During certain intervals, they may favour a gradual decline in carbon dioxide that adds to the cooling driven by weathering of tropical continents. As the Neoproterozoic progresses, evidence from rocks and geochemical signals suggest that Earth experiences repeated glacial episodes. In some ice reaches into mid-latitudes on multiple continents. These glaciations are more extensive than many earlier ones, yet between them, the climate relaxes into milder periods, during which ice retreats and shallow seas again cover low-lying regions. The alternation between cold and less cold intervals points to a climate system that is sensitive to relatively small shifts in greenhouse gases, solar distribution, and surface reflectivity. Each glaciation tests the balance between processes that cool and those that warm. With continents positioned in ways that favour strong weathering in the tropics, and with life quietly drawing down carbon from the surface environment, the long-term baseline temperature continues its slow trend downward. On the compressed 24-hour clock of Earth history, the later Neoproterozoic occupies the minutes after about 8 in the evening. The planet has already sustained life for billions of years. Bacterial films and other single-celled organisms coat sediments, rocks, and shallow seabeds. Complex multicellular life has not yet become widespread. The climate now hovers near thresholds at which familiar feedbacks may behave differently. Polar and high mountain ice have grown more extensive than in many earlier times, yet broad swaths of ocean at lower latitudes still exchange heat and gases freely with the atmosphere. Clouds form over warm waters, reflect some sunlight, and trap some heat, adding another layer of complexity to the energy balance. In this state, the Earth system is both stable on human timescales and precarious on geological ones. The balance between incoming solar energy, the insulating effect of greenhouse gases, the reflective power of ice and snow, and the rates at which rocks and life remove or add carbon to the surface environment is close to a point where modest additional changes can lead to larger responses. In the hundreds of thousands of years and millions of years that follow, this near balance will be disturbed in ways that allow glaciations of greater reach to begin transforming the global atmosphere and climate from this relatively mild world into one where cooling feeds upon itself on a far grander scale. Around the Neoproterozoic Earth, a thin layer of gases envelops the planet and helps decide how much of the sun's energy stays near the surface. This atmosphere contains nitrogen as its main component, with smaller amounts of oxygen, water, vapor carbon dioxide, and other gases. Among these greenhouse gases, such as carbon dioxide and water vapor, play a central role in setting temperature. Incoming sunlight, mainly in visible wavelengths, passes through the clear air and reaches the surface. There, land and water absorb much of this energy and warm up. In response, the surface emits energy back upward as infrared radiation. Greenhouse gases absorb part of this outgoing infrared and re-emit it in all directions, including back downward, which keeps the lower atmosphere and surface warmer than they would be in the absence of such gases. This greenhouse effect is not a rare or exceptional feature, but a normal part of Earth's climate system. Without it, the average surface temperature would sit well below the freezing point of water, and global oceans would be far more prone to complete icing. With it, temperatures stay in a range that supports liquid water across much of the planet. In the long lead up to Snowball Earth, this balance is controlled by slow exchanges of carbon between the atmosphere, oceans, rocks, and the planet's interior. Volcanoes bring carbon from the mantle to the surface by releasing carbon dioxide and other gases. When lavas erupt and dega, or when volcanic vents bubble carbon that was once stored deep inside Earth, enters the air and oceans. Over millions of years, this volcanic input maintains a background level of greenhouse gases. At the same time, processes at the surface steadily remove carbon dioxide from the air. When rain falls through the atmosphere, it picks up carbon dioxide and becomes slightly acidic. As this rainwater flows over and through rocks, it reacts with minerals. These reactions break down silicate minerals and form dissolved ions that rivers carry to the sea. In the oceans, marine organisms and inorganic processes combine some of these dissolved substances into carbonate minerals such as calcite. These carbonates settle on the seafloor, producing layers of sediment that slowly turn into rock. Carbon that began in the atmosphere as a gas ends up locked into solid minerals on the ocean floor. Over very long times, some of these carbonate-bearing rocks are carried back into the interior by subduction of oceanic crust, closing the cycle. This long-term carbon cycle acts as a broad climate regulator. If temperatures rise, weathering reactions on land tend to speed up because warm and wet conditions promote faster breakdown of minerals. Increased weathering removes carbon dioxide from the atmosphere more quickly, reducing greenhouse warming and countering the initial rise in temperature. If temperatures fall, weathering slows in many regions, volcanic input can then outpace removal, and carbon dioxide builds back up, strengthening the greenhouse effect and pushing temperatures upward. In many intervals of Earth history, this feedback keeps the climate within a band that avoids extreme cold or heat. During the Neoproterozoic, however, the positions of continents and the state of the biosphere gradually alter how this regulator behaves. As plate motions bring large land masses into tropical and subtropical latitudes, wide areas of rock lie under intense sunlight and heavy rainfall. Rivers on these equatorial continents erode deep weathering profiles, and chemical reactions between rainwater and exposed minerals proceed at high rates. Over spans of tens of millions of years, this tropical weathering can remove carbon dioxide from the atmosphere more efficiently than in times when most continents lie at higher latitudes. Meanwhile, in the oceans, microbial life plays its own part in the carbon cycle. Photosynthetic microorganisms, including cyanobacteria, draw carbon dioxide from seawater, use its carbon to build organic matter and release oxygen. In some shallow environments, these microbes form layered structures where sticky films trap sediment grains and promote the precipitation of carbonate minerals. Over time, these repeated layers build up into stromatolites and related reef-like formations that incorporate large amounts of carbonate. In doing so, they sequester carbon in solid form on the seafloor. When scientists examine ancient carbonate reefs in places such as present-day Australia and other regions, they sometimes test small pieces of these rocks with weak acid. The acid reacts with carbonate minerals and releases carbon dioxide as tiny bubbles. This reaction shows that carbon, which once circulated in the atmosphere and ocean, now resides in solid rock. In the time before Snowball Earth, microbial activity of this kind, combined with high rates of chemical weathering on low-latitude continents, tends to draw down the amount of carbon dioxide in the air and surface ocean. As carbon dioxide declines, the greenhouse blanket around Earth grows thinner. The atmosphere still contains water vapour, which is itself a greenhouse gas, but the amount of water vapour depends strongly on temperature because warm air can hold more moisture than cold air. As cooling proceeds, the air's capacity for water vapour falls, and its actual water vapour content decreases. This further reduces greenhouse warming and allows more infrared radiation to escape to space. The combined effect of declining carbon dioxide and decreasing water vapour slowly shifts the global energy budget. For a given amount of incoming sunlight, more of the outgoing heat now leaves the planet instead of being held near the surface. Average temperatures edge downward. High-latitude regions, which receive less direct sunlight, respond the most. Winters lengthen and intensify there. Snow that accumulates during the dark months melts less completely in the following summer. Patches of perennial snow begin to persist in places where seasonal snow once vanished each year. On upland terrain and mountain ranges, glaciers thicken and creep downslope. Sea ice around polar coastlines grows somewhat more extensive and remains for longer seasons. Cloud patterns also adjust as the climate cools. Warm surfaces drive the strong evaporation that feeds deep convective clouds in the tropics. As sea surface temperatures fall, evaporation rates drop and some convective activity weakens. In cooler conditions, more low clouds can form in some regions. Low bright clouds reflect a significant fraction of incoming sunlight back to space, which cools the surface beneath them. High thin clouds, in contrast, can have a net warming effect because they allow much sunlight through, but trap some outgoing infrared. The relative amounts and types of clouds and their regional distributions become important in deciding how the cooling trend plays out. In a gradually cooling world, small shifts in cloud cover can either offset or enhance the drop in temperature. At this stage, Earth is not yet fully locked into extreme glaciation. Oceans at low latitudes are still largely ice-free. Dark seawater absorbs much of the sunlight that reaches it, especially when the sun stands high in the sky over tropical regions. Atmospheric circulation continues to move heat from equator to poles. Storm systems transport moisture and energy along familiar tracks. The atmosphere remains an active medium with winds, clouds, and precipitation, cycling energy and water between surface and sky. Yet measured over millions of years, indicators in the rock record and in geochemical signals show that the background concentration of carbon dioxide has declined significantly from earlier levels. This means that the same amount of incoming solar energy now results in a cooler global mean temperature. Local cold spells, which in a warmer climate would be temporary and limited in reach, grow into longer and more extensive glacial episodes. Ice sheets in high latitudes expand farther toward mid-latitudes than before. In some reconstructions, glaciers stretch across large parts of continents that lie at modest latitudes, leaving behind deposits that bear the marks of glacial activity. Paleomagnetic measurements of rocks from these glacial deposits later reveal that they formed at surprisingly low latitudes, suggesting that substantial ice had reached zones that normally favour warmth. In this atmospheric context, the climate system approaches a fragile point. Greenhouse gases have been drawn down by a combination of vigorous rock weathering on low-latitude continents and long-running biological processes in the oceans. The air holds less water vapour because of the progressive cooling. The balance between absorbed sunlight and outgoing heat radiation is close to a threshold where further modest cooling can bring about larger changes in ice cover and reflectivity. On geological timescales, this state does not last indefinitely, because other processes such as volcanic degassing continue to operate. However, in the interval leading into Snowball Earth, the atmosphere and climate drift into a configuration where reduced greenhouse warming and altered cloud and moisture patterns allow ice to gain ground more easily than in many previous eras. With the greenhouse blanket thinned and the energy budget shifted toward greater loss of heat, to space the next advances of snow and ice at high and mid-latitudes will have consequences that reach beyond their initial regions, influencing the entire planet's ability to store and release solar energy. As the Neoproterozoic climate continues to cool, the reflectivity of Earth's surface becomes a more important part of the energy balance. This reflectivity, called albedo, varies from one surface type to another. Fresh snow and thick sea ice reflect a large fraction of incoming sunlight back into space. Dark ocean water and dense forests absorb most of the sunlight that reaches them. Bare rock and dry soil fall in between. When the planet is relatively warm, the brightest surfaces are limited to polar and high mountain regions, and their global influence on albedo is small. In a cooler world, snow and ice extend farther away from these confined zones, and their impact on the total amount of absorbed solar energy increases. At the same time, sea ice around high-latitude coastlines thickens and stays in place for more of the year. In open water, waves break incoming sunlight and allow it to penetrate below the surface where it is absorbed efficiently. Sea ice, especially when covered by snow, sends much of this energy back into space. As the ice margin moves to lower latitudes, regions that once absorbed sunlight now return more of it, reducing the heating of the surface and lower atmosphere. This change strengthens the cooling trend that began with the gradual decline of greenhouse gases. The albedo feedback is direct. Cooling allows more snow and ice to persist. More snow and ice increase the planetary albedo. A higher albedo means less solar energy is absorbed, which leads to further cooling. In many climate states, this feedback operates in a limited way, because other processes counterbalance it. For example, as the planet cools and weathering slows on land, volcanic emissions can rebuild carbon dioxide in the atmosphere over long times. Warmer intervals then follow and ice retreats. However, when continents lie in low latitudes and cooling is already advanced, the albedo feedback can push the system toward a threshold. Once ice reaches certain latitudes, additional small changes can produce larger responses because the incoming sunlight there is strong, and the contrast between dark water and bright ice is large. Cloud cover adds another layer to this evolving picture. Clouds both reflect sunlight and trap outgoing infrared radiation. Low, thick clouds tend to cool the surface beneath them by reflecting a large portion of sunlight. High, thin clouds tend to warm the surface by allowing sunlight through while absorbing some outgoing heat. The net effect of clouds depends on their type, height, thickness, and distribution. In a world that is cooling, changes in sea surface temperature, atmospheric circulation, and humidity alter where and when different kinds of clouds form. Over warmer open oceans, evaporation supports deep convective clouds and a rich cycle of rainfall. As the oceans cool and ice occupies a larger fraction of high-latitude waters, evaporation decreases in those regions, and the character of cloudiness changes. Above bright ice, low clouds can further increase the reflection of sunlight, enhancing cooling. In some areas, clear dry air dominates, allowing more infrared radiation to escape to space. The combined changes in surface albedo and cloud properties gradually shift the balance between incoming and outgoing energy. At high latitudes, long winters with weak sunlight allow ice and snow to persist and grow. In spring and summer, when the sun climbs higher in the sky, the bright surface continues to reflect much of its energy. The seasonal melting that once limited the growth of glaciers now becomes less effective. Ice sheets on land thicken and spread. Sea ice around the poles extends into lower latitudes and lasts longer into the warmer seasons. Each advance in ice cover modifies the climate above it, reinforcing the trend. Climate models that simulate these processes show that if sea ice extends beyond a certain latitude, often estimated around 30 degrees from the equator, the albedo feedback can drive a rapid expansion of ice toward lower latitudes. In such a state, the gain from additional ice outweighs many of the stabilizing influences that usually act on climate. The system moves toward a configuration where ice becomes the dominant surface over most of the globe. The transition from a partly glaciated world to an almost fully ice-covered planet does not occur in a single instant, but on geological timescales it is fast compared with the slow drifts that preceded it. Over perhaps hundreds of thousands to a few million years, advancing ice shifts the global mean albedo to much higher values. With more solar energy reflected, the average surface temperature falls to well below the freezing point of seawater. The oceans lose heat to space through the thin shell of atmosphere above, and their upper layers approach the freezing point over wide areas. In the atmosphere during this advance, water vapor content drops because colder air holds less moisture. The greenhouse effect from water vapor therefore weakens, and clear sky regions become more effective at radiating heat away. Carbon dioxide remains present, but at reduced levels because of prior long-term removal by weathering and biological processes. Without significant new additions from volcanic activity or other sources on short timescales, the diminished greenhouse blanket cannot offset the strong cooling caused by high albedo and low water vapor. Wind patterns also adjust as the surface cools and gradients in temperature change. The contrast between warm tropics and cold poles, which drives many mid-latitude storms, becomes less sharp in some layers of the atmosphere as the tropics themselves cool. Jet streams may shift in position and strength. Storm tracks adjust and the distribution of snowfall changes. Yet the overall tendency remains that more of the precipitation that does fall in cold regions adds to ice mass rather than being removed by melting. Over ocean areas that were once stormy and ice-free, the formation of continuous sea ice dampens, exchange of heat and moisture between water and air, leading to calmer conditions above the frozen surface. As glaciation deepens, the vertical structure of the atmosphere reflects the new state. Near the surface over large regions, temperatures stay far below freezing. The lower atmosphere becomes more stable with less mixing between surface air and higher layers. Temperature inversions, where temperature increases with height over some interval, instead of decreasing, can form above the ice, trapping cold air close to the surface. Higher in the troposphere and lower stratosphere temperatures respond to changes in radiation patterns and to reduced water vapor and cloud formation. The air grows drier overall, and precipitation becomes rare in many interior continental regions that are already locked in ice. At the global scale, the balance of radiation at the top of the atmosphere shifts to one in which outgoing infrared exceeds absorbed solar energy for an extended period. As long as this imbalance persists, the planet continues to cool until a new equilibrium is reached at much lower surface temperatures. In the Snowball Earth state, most of the sunlit surface that the atmosphere registers is bright ice or snow. Only small areas of exposed rock or thin, seasonally open water remain, and their contribution to absorbing sunlight is limited. The atmosphere above this frozen planet is cold thin in water vapor and relatively simple in its circulation when compared with the more complex patterns of a warmer world with strong contrast between land and sea. It remains, however, an active layer that continues to transport trace gases, interact with incoming and outgoing radiation, and sit at the center of the energy exchanges that will eventually allow the climate system to change again when internal and external forcings shift in new ways over long spans of time. Over a fully glaciated Neoproterozoic Earth, the atmosphere continues to wrap the planet in a thin but persistent shell. The composition of this shell remains dominated by nitrogen, with smaller amounts of oxygen, carbon dioxide and trace gases, but its behavior over the frozen surface differs from that of a warmer world. With most oceans and continents covered by thick ice and permanent snow, the lower atmosphere becomes colder, drier, and more stratified. Near the surface, temperatures in many regions stay far below the freezing point for long stretches of time. Cold air is dense and it tends to pool over the broad ice sheets, forming shallow layers that resist vertical mixing. The amount of water vapor in the air drops sharply because cold air can hold much less moisture than warm air. As a result, clear skies become common over the interior of the ice sheets, and clouds where they do form are often thin and confined to particular belts. The hydrological cycle slows. Evaporation from the surface of the oceans is greatly reduced where thick sea ice stands between water and air. On land, there are few exposed liquid water surfaces, from which moisture can enter the atmosphere. Precipitation continues, but at much lower rates over many regions than in earlier times. Snowfall becomes the main form of precipitation, and in the coldest interior zones of the ice sheets, even snowfall can be rare, turning them into cold deserts in which accumulation is slow. Near the edges of the ice sheets and in narrow zones where temperature and topography allow more active weather systems, snowstorms still occur, and winds can be strong, redistributing fine snow across the icy surface. At the scale of the whole planet, the pattern of winds adjusts to the new temperature structure. In a temperate world, the contrast between warm tropics and cold poles drives large circulation cells that transport heat and moisture. In the Snowball Earth state, the tropics themselves are greatly cooled, and the equator to pole temperature gradient weakens near the surface, though it may remain present higher in the atmosphere. The Hadley circulation, which normally carries warm air aloft near the equator and brings it down again at subtropical latitudes, is altered by the presence of high albedo surfaces across all latitudes. Rising motion over warm ocean surfaces becomes limited because there are few such surfaces left. Convection weakens in many areas, and large parts of the atmosphere become more stably stratified. Over the great ice sheets, especially on the flanks that slope gently toward lower latitudes, cold, dense air tends to flow downhill under gravity. These katabatic winds can reach high speeds, particularly where they are funneled through valleys or across broad, smooth slopes. They sweep dry, frigid air from the interior toward the margins of the ice. As they do so, they can pick up fine snow grains and any dust that has settled on the ice, blowing this material outward. Near the margins, where ice meets any exposed rock or thin zones of seasonal melting, such winds may help keep the surface clear of fresh snow by constantly scouring it. In the band of latitudes near the equator, where the last edges of the great ice sheets from each hemisphere may once have approached one another, the atmosphere adjusts further. Here the sun stands high in the sky at some times of the year, and even over an icy surface it can deliver substantial energy. The air above these low latitudes is still cold compared with that of a warm Earth, but it can be relatively less cold than over the poles. This contrast can maintain a weakened but still present belt of ascending motion, which in a warmer climate corresponds to the intertropical convergence zone. On a Snowball Earth, instead of rising over dark warm oceans, air rises over bright cold ice, or over narrow leads of dark water, where sea ice may occasionally fracture. Clouds in this belt may form as thin layered decks, rather than as towering convective structures reflecting some sunlight and exerting a modest influence on the energy budget. Above the entire planet, the reduced water vapor content of the atmosphere alters its role as a greenhouse agent. Water vapor is a powerful absorber of infrared radiation, and its decrease allows more heat to escape to space. Carbon dioxide, though, present at lower concentrations than in many earlier times, continues to absorb and emit infrared radiation. Over the long duration of the Snowball state, volcanic activity from the interior emits carbon dioxide into the air. Because most surfaces are frozen, and weathering reactions on exposed rock are greatly suppressed, the immediate removal of this gas by chemical processes is limited. The atmosphere therefore slowly accumulates carbon dioxide, but this accumulation is spread over millions of years, and for much of the Snowball interval the surface remains extremely cold. In the short term, aerosols and volcanic particles injected into the upper atmosphere by eruptions can further complicate the radiative balance by reflecting sunlight or interacting with clouds, though their residence times aloft are limited compared with the vast span of the glaciation. The vertical temperature profile of the atmosphere over a Snowball Earth reflects the influence of a bright surface and thin water vapor. Close to the ground, temperature often increases with height over a shallow layer, forming an inversion, because radiative cooling at the ice surface chills the air immediately above it. This inversion suppresses mixing, so dust or water vapour released near the surface tend to remain trapped. Higher in the troposphere temperatures decrease with height in a more familiar pattern, but the overall depth of the troposphere can be reduced in cold conditions. The stratosphere above may remain influenced by absorption of ultraviolet radiation by ozone, though oxygen and ozone levels in the Neoproterozoic are still evolving compared with modern values. Winds at high altitudes, including jet streams, are shaped by the distribution of temperature with latitude and height. With less heat contrast at the surface, some jets may be weaker or located at different heights, and the pathways of high-altitude waves that move through the atmosphere change accordingly. Dust in the atmosphere during Snowball Earth likely comes from limited sources: exposed rock outcrops, occasional volcanic eruptions, and zones where strong katabatic winds abrade the surface of the ice, and any underlying sediments can all release fine particles into the air. Once aloft, these particles can travel long distances before settling. They act as nuclei for cloud droplets or ice crystals, and can modestly influence cloud properties. Over time, some of this dust settles back onto the ice sheets, forming thin, dark layers that alter surface brightness in local areas. These layers can marginally increase absorption of sunlight where they accumulate, but on the global scale, the overwhelming presence of bright snow-covered ice keeps the planetary albedo high. In this frozen state, the atmosphere carries only faint traces of the vigorous water cycle that characterizes warmer climates. There are no large expanses of open warm ocean to feed deep convective storms. Tropical cyclones, as seen in later eras, do not form. Thunderstorms are rare and confined to limited regions where temperature contrasts and moisture still allow them. Instead, much of the atmospheric motion consists of broad, slow flows, gentle subsidence over the interiors of ice sheets, and bands of stronger wind along margins and in the upper troposphere. Despite its subdued nature, the atmosphere remains the medium through which energy and gases are transported around the globe. It continues to radiate heat to space to receive sunlight to carry trace gases from volcanoes, and to exchange limited amounts of moisture and carbon dioxide with the surface. Its cold, dry state is both a response to the presence of global ice and a participant in maintaining that ice through its control of temperature precipitation and radiative flows. In the long span of the snowball interval, this air above the frozen world holds the planet in a stable but extreme climatic condition, until slow changes in internal and external factors gradually alter its composition and energy balance once more. On the continents of a snowball Earth, the surface is dominated by ice that has grown from small mountain glaciers into vast interconnected ice sheets. The process begins long before full global glaciation, when cooling climates allow winter snow in high latitudes and high elevations to survive the summer. Each year new snow falls on top of older layers. Under its own weight, the snow slowly compacts. Individual snow crystals become more tightly packed airspaces shrink, and the material transforms first into a granular intermediate known as firn, and then into dense glacial ice. This transformation can take decades to centuries in regions of steady accumulation. As the ice thickens, it begins to deform and flow under the influence of gravity. Although ice is solid under high pressure, and over long timescales, it behaves like a very slow-moving fluid. In the central parts of an ice sheet where accumulation is greatest and the surface stands high above sea level, ice spreads outward in all directions. At the margins, the flowing ice descends toward lower elevations, forming outlet glaciers and ice streams that funnel mass from the interior toward the edges. The rates of flow vary with ice thickness, temperature, and the nature of the underlying bed, but typical velocities range from a few meters per year in cold, slow-moving areas to hundreds of meters per year in fast-flowing ice streams. On the scale of human experience, this motion is almost imperceptible. On geological timescales, it is sufficient to reshape broad regions of the surface. Beneath the ice, the contact between the moving mass and the underlying rock or sediment is an active zone. Where the base of the ice is at or near the pressure melting point, a thin film of liquid water can exist between ice and bed. This water acts as a lubricant, allowing the glacier to slide. Where the base remains colder, the ice may be frozen to the substrate and moved mainly by internal deformation. In either case, the friction and pressure at the base allow ice to pluck blocks from the bedrock and to drag rock fragments along. These fragments, from fine rock flour to large boulders, become embedded in the lower part of the ice and in a layer of debris-rich ice close to the base. As the ice moves, these embedded materials act like tools that grind and scour the underlying surface, creating striations, grooves, and smoothed forms on the bedrock. Over long periods, the interaction between ice-embedded debris and the bed produces characteristic landforms. Bedrock knobs are worn into streamlined shapes with gentle stoss sides that face the direction of ice advance, and steeper lee sides where plucking removes larger blocks. Ridges and mounds of unsorted debris known as moraines accumulate where ice margins stand still for extended periods, or where they retreat. In valleys, glaciers carve cross-sections that change from the V-shaped profiles cut by rivers to U-shaped troughs, with steep walls and flat or gently sloping floors. On a Snowball Earth, these processes are not confined to single mountain ranges or high-latitude fringes. As cooling intensifies and snow accumulates over larger areas, separate ice caps on different parts of a continent expand and merge. High plateau regions that once shed snow in seasonal thaws become centers of persistent accumulation, feeding ice that spreads outward and eventually connects with neighboring ice bodies. Over time, broad, continuous ice sheets cover much of the land surface, reaching thicknesses of several thousand meters in their central domes. The weight of these massive ice sheets depresses the crust beneath them. The lithosphere responds elastically and plastically, flexing downward under the load. Around the margins of the ice regions beyond the main load may rebound slightly upward. This adjustment, known as isostatic response, alters local sea levels and the gradients over which ice flows. As loading and unloading proceed over long timescales, they interact with the pattern of glacial advance and retreat. In coastal regions, the ice sheets often reach the edges of the continental shelves. Where ice extends onto these shelves and into shallow marine basins, it forms floating extensions called ice shelves, supported by seawater beneath. At the grounding line, where the ice sheet transitions from resting on the bed to floating, the base of the ice loses direct contact with the substrate. Stresses due to bending ocean tides and currents within any available seawater can promote fracturing, and large blocks may carve away from the front of the ice shelf as icebergs. These icebergs contain within them the debris that the glacier has picked up along its journey over land. As they drift, they gradually melt and release their rock cargo, which falls into the water column and settles on the seafloor. In later times, these isolated stones within otherwise fine-grained marine sediments become drop stones, a distinctive signature of glacial influence. On the continents themselves, the surface of the ice sheets is not a uniform plane. Accumulation zones at high elevations receive regular snowfall which is compacted into new ice. Ablation zones nearer the margins lose mass through sublimation, limited melting in some seasons calving into marine or subglacial basins, and wind-driven redistribution of snow. Crevasses open where ice accelerates or flows over irregular topography, marking zones of high strain. Wind scours some areas, leaving hard, smooth surfaces of blue ice, where older ice is exposed. In other regions, snowdrifts fill depressions and build cornices along ridges. Across this frozen terrain, temperature gradients and wind patterns shape the microtopography of the surface, but on the scale of continents, the dominant feature is the continuity of ice cover. The movement of ice across the buried landscape continues to transport rock and sediment far from their sources. Boulders from one mountain belt can be carried hundreds or even thousands of kilometers before being deposited. When the ice eventually retreats, such erratic blocks rest on bedrock of very different composition, marking the reach of former glaciers. Layers of till, a mixture of clay, silt, sand, gravel and larger stones accumulate at the base and front of the ice, plastered onto the substrate or heaped into moraines. In the snowball state, much of this deposition takes place beneath ice that remains present for long spans of time, so the evolving landforms are largely hidden from the atmosphere. The pressure at the base of very thick ice can bring basal ice near its melting point even when the surface is extremely cold. Geothermal heat from the interior contributes to this warming from below. In some regions, meltwater generated at the base may collect in subglacial lakes or flow through networks of channels beneath the ice sheet. These waters can transport fine sediments and abrade the substrate, further carving tunnels that are later preserved as sediment-filled eskers when the ice is gone. In other regions, the base remains frozen, and the ice there moves mainly through internal deformation, leaving different patterns of erosion and deposition. On timescales of millions of years, the interaction between ice dynamics, isostatic adjustment and surface erosion reshapes entire continental blocks. Mountain ranges are lowered by glacial carving, valleys are widened and deepened, and large regions of previously varied topography become smoother under the repeated passage of ice. Yet during the snowball interval itself, these changes proceed beneath an active but relatively uniform icy cover that spans latitude bands far broader than in more familiar ice ages. From a planetary perspective, the continents under snowball conditions present to space a surface largely covered in bright ice, with only limited patches of exposed rock protruding above the ice sheet, as nunataks in some high mountain areas. These isolated rocky peaks may interrupt the glacial flow locally and shed small amounts of debris onto the ice, but their influence on the broad pattern of ice cover is minor. The key feature of this stage is the dominance of thick flowing ice on land shaped by gravity, temperature and basal conditions, interacting with the crust beneath and slowly rearranging the shape of the continents, while providing large quantities of debris to the adjacent marine margins. All of this occurs while the ice continues to expand and consolidate, preparing the way for the next phase in which sea ice over the oceans reaches to lower and lower latitudes. As global cooling deepens and continental ice sheets consolidate in the Neoproterozoic, the oceans respond through the steady expansion of sea ice from high toward low latitudes. At first, the formation of sea ice follows patterns similar to those seen in more familiar ice ages. In polar regions, autumn and winter bring long nights and strong heat loss from the upper ocean. When the surface water cools to its freezing point, a thin skin of ice forms. This new ice begins as a fragile cover of needle-like crystals and small plates that float and jostle in the waves. Over time, as the surface loses more heat, these crystals weld together into continuous sheets. Snow falls on top, insulating the underlying ice and altering its texture and reflectivity. In coastal areas, this seasonal ice attaches to landfast ice along the shores and to the floating edges of outlet glaciers from the continents, building a connected fringe around the polar basins. The formation of this ice cover changes how the ocean interacts with the atmosphere. Where open water once released heat and moisture into the air, the ice now acts as a barrier. Turbulent exchanges diminish, and the overlying air mass cools further. Winds can still push the ice around, compacting it into ridges where flows collide, and tearing it apart into leads where cracks open. These leads expose narrow strips of dark water between the white surfaces. They can briefly absorb more sunlight than the surrounding ice, and release heat and vapor to the atmosphere. But as the climate trend remains toward cooling, even these leads tend to refreeze. As the years and centuries pass, the zone of multi-year sea ice thickens and extends equatorward, moving from polar latitudes into mid-latitudes. The advancing front of sea ice is not a smooth line, but a broad belt, with a mix of consolidated pack ice, new ice, and scattered open leads. Waves at the ice edge are damped by the ragged fringe of floes, and storm-driven swell loses energy before it can penetrate far into the pack. In winter seasons, the ice edge advances quickly. In summer, it retreats less and less each year. The net effect is a gradual shift of the average position of the ice margin toward lower latitudes. As this margin moves, it redefines where the planet presents bright reflective surfaces to the sun. In regions that once absorbed a large fraction of incoming sunlight, the presence of sea ice and overlying snow now sends much of that energy back to space. The local ocean surface remains close to the freezing point, unable to store as much heat as warmer waters once did. The atmosphere above cools, further reinforcing the spread of ice. This is the sea ice component of the albedo feedback operating alongside the brightening of continents under spreading ice sheets. Floating ice also carries with it traces of the land from which it originates. Along many coasts, the termini of outlet glaciers that reach the sea break off as icebergs. These icebergs incorporate layers and pockets of rocks, gravel, and finer sediment that the glaciers have eroded from the continental interior. Once in the ocean, currents and winds move the icebergs across the surface. As they drift, they gradually melt from below and from their sides, thinning until they finally disintegrate. When the embedded rocks are released, they sink through the water column and come to rest on the seafloor, often many hundreds or thousands of kilometers from their source. During Snowball Earth, the extension of sea ice to lower latitudes allows icebergs and sea ice rafts to travel across wide oceanic distances. Even when the surface becomes almost entirely ice-covered, fractures, pressure ridges and zones of thinner ice continue to form, and ice blocks with debris can be moved along these pathways. The scattered deposition of such debris will later appear in the sedimentary record as isolated stones within otherwise fine-grained layers, providing evidence that floating ice once passed overhead. At the advancing front of the sea ice, the interaction with the atmosphere remains intense. When new ice forms from seawater, salt is rejected from the growing crystals and concentrated in the thin liquid film between them. This process, known as brine rejection, produces cold, salty water that is denser than the underlying seawater and tends to sink. In a world that is not yet fully sealed by ice, this process helps drive vertical mixing and influences the formation of deep and intermediate water masses. In the approach to a snowball state, the area over which new ice forms increases greatly as the ice margin moves equatorward. Large volumes of cold saline water can form near the surface and descend, while the overlying ice cover reduces wind-driven mixing and the direct input of heat from the atmosphere. The ocean thus cools from the top downward over broad regions. From the perspective of the surface, the growing sea ice appears as a continuous shield that smooths out the ocean's waves and imposes a new roughness pattern, composed of ridges, hummocks, and pressure features within the ice itself. Snow accumulates on these surfaces, thickening the insulating layer and further separating the ocean below from the air above. In places where strong winds blow persistently from the interior of the ice-laden continents toward the ocean, the sea ice can be pushed away from the coast, creating recurring zones of open water known as coastal polynyas. These areas act as local sources of heat and moisture to the atmosphere and as sites of vigorous new ice formation. However, as global temperatures continue to decline and the supply of heat from the open ocean dwindles, even polynyas tend to become smaller and more ephemeral. For longer and longer portions of the year, and eventually for entire years, sea ice can remain attached to the coast and stretch unbroken far offshore. As sea ice spreads into subtropical and ultimately tropical latitudes, the geometry of the planet amplifies its climatic impact. Near the equator, the sun's rays are more direct on average, and the potential for absorption of solar energy is greatest. Under pre-snowball conditions, these regions are home to the warmest surface waters, driving strong evaporation and deep atmospheric convection. In a snowball configuration, thick snow-covered sea ice occupies this band instead. The same intense sunlight now falls on a reflective surface, and much of it is reflected back into space. The net gain of heat in the tropics drops sharply, reducing the temperature difference between equator and poles, and shifting the balance of the entire climate system. Climate model studies suggest that once sea ice advances beyond a certain critical latitude, the combined increase in planetary albedo and the existing low greenhouse gas levels make it difficult for the system to return to a partly ice-covered state without a significant external or internal forcing. The planet moves into a stable configuration where sea ice extends from one continent to another across what were once open tropical seas. During full snowball conditions, the thickness of sea ice over the central parts of the oceans may reach hundreds of meters or more, especially when accumulation of snow and ice persists over millions of years. The surface of this ice is cold and rigid on short timescales, but over longer spans it can deform under stresses imposed by winds, the flow of underlying ice, and the slow creep driven by gravity along gentle slopes set by variations in ice thickness and ocean surface height. Ridges form where flows converge, piling ice blocks into linear features that rise above the surrounding plain. In the troughs between ridges, snow can accumulate and drift, creating subtle relief that influences how wind and radiation interact with the surface. From pole to equator, and back to the opposite pole, the ocean surface becomes a continuous mosaic of these icy features. Islands and submerged continental shelves lie hidden beneath the ice cover, their outlines detectable only through the way the ice surface responds to underlying topography. Along former continental margins, grounded ice shelves extend seaward from the main ice sheets, merging into the thicker pack. There are no large expanses of dark open water left to break the continuity of the bright surface. The air above flows across a nearly uniform skin of ice and snow, while the ocean below is sealed away from direct contact with the atmosphere. In this stage, the sea ice has completed its march from the poles to the tropics, transforming the appearance and energy balance of the planet's surface, and closing the last low latitude gaps through which the ocean and atmosphere once communicated directly. Beneath the weight and motion of the ice on a snowball Earth, the solid surface of the planet is steadily reshaped. On the continents, thick ice sheets move under gravity, carrying within their lower layers a mixture of rock fragments that have been pried from the bed. At their bases, ice masses press against the underlying substrate with great force. Where the ice is at or near the pressure melting point, a thin film of meltwater lubricates the contact, allowing the ice to slide. Rock fragments lodged in this basal ice and in the thin water layer act as tools that grind, scratch, and chip at the bedrock. In regions where the ice flows over resistant rock, this action produces smooth, gently sloping surfaces on the upstream side and steeper, more irregular forms on the downstream side as blocks are plucked away. These features, known as streamlined knobs and similar shapes, are aligned with the direction of ice motion and record the flow paths of the ice sheets. Across large areas, the bedrock is polished and scored. Long linear grooves and fine striations cut into the rock surface show where debris-loaded ice dragged across it. In some places, parallel sets of these marks cross at different angles, indicating changes in the direction of flow over time. Finer grinding reduces rock to silt, and clay-sized particles called rock flour, which can be carried within the ice, or flushed away by meltwater and deposited elsewhere. As the ice sheets spread, they overrun landscapes that previously had river valleys, hills, and plains. River-carved valleys with V-shaped cross-sections are widened and deepened, taking on U-shaped profiles with flat bottoms and steep straight sides. In coastal mountain regions where glaciers descend from high plateaus toward the sea, these valleys may be cut below the level of future sea level, forming over-deepened troughs. When ice retreats in later times and the ocean floods these valleys, they can become fjords, but during the snowball interval the ice fills them and extends beyond their mouths as outlet glaciers and floating ice tongues. Lower relief landscapes also feel the imprint of the ice. Where formerly rolling terrain lay under a thin soil and weathered rock cover the passage of ice strips away loose material and planets' ridges. Depressions are carved by focused erosion along zones of weaker rock or former drainage lines. Networks of subglacial meltwater channels, where they exist beneath warm-based ice, further incise the bed-forming tunnel-like features that later become sites for sediment deposition. The result is a patchwork of smooth surfaces, streamlined ridges and enclosed basins. In many places, the ice does not simply erode, it also deposits. The debris that is entrained in the ice is released when the ice deforms, melts at its base, or stagnates at its margins. Close to the base, unsorted mixtures of clay silt, sand, gravel and boulders are pressed against the bedrock and left as a dense compact material called till. Till blankets low-lying areas, fills hollows and forms irregular mounds. Along stable ice margins it accumulates into ridges known as moraines, recording positions where the ice front paused for long periods. In other areas, ramps and hummocks of till are smeared along the direction of flow, forming drumlin fields and related features. All of these deposits are poorly sorted with sharp-edged stones of different sizes intermixed, reflecting the direct release of material from the ice, rather than sorting by water. At the edges of the continents where ice advances onto continental shelves and into shallow seas, the interaction between land-based ice and the marine environment produces additional signatures. Outlet glaciers may feed into broad grounded ice shelves that extend over the submerged shelf and out toward deeper water. As these shelves flex and crack under stresses from tides, currents, and their own weight blocks break away and form icebergs. These icebergs carry in their lower parts and bases a cargo of stones and sediment scraped from the interior. As they drift across the surface of the ocean, they release this cargo in a scattered pattern. Each drop of a stone from a melting iceberg delivers a piece of distant bedrock to the seafloor where it lands on top of finer sediments that are settling from the water column. Over time, this process produces layers of mud and silt with isolated pebbles and boulders embedded within them. These are the drop stones that later provide clear evidence of ice rafting. During Snowball Earth, the reach of sea ice and icebergs extends far beyond traditional polar and subpolar zones. Icebergs carved from continental margins may travel thousands of kilometers over what are now low and mid-latitude seafloors. As they melt from below in slightly warmer waters near lower latitudes, they drop their debris load into environments that in non-glacial times would not receive such coarse material. Similarly, even where sea ice forms directly from freezing seawater rather than from glacier ice, it can trap small rock fragments and sediment picked up from coastal zones or from dust that settles on its surface. When this sea ice later melts, these particles sink and join the accumulating blanket of seafloor sediment. While the present focus remains on the surface and near-surface rocks, it is clear that the snowball state modifies both exposed and submerged parts of the solid earth. On land, the ice abrades and sculpts the bedrock, stripping away pre-existing weathered layers and leaving fresh rock surfaces. It rearranges sediment, moving it from uplands to lowlands and from the interior toward the coasts. It piles some of this sediment into ridges and sheets that follow the ice flow lines. On submerged shelves, the grounded ice scours the seafloor, carving grooves and ridges into soft sediments and even into consolidated substrates. When the ice front eventually retreats, these marks remain as clear indications of its former presence. The sheer spatial scale of these processes during Snowball Earth is unusual when compared with other glacial periods. Instead of being confined to high latitudes and high mountains, glacial erosion and deposition reach into regions that under more typical climatic conditions would be dominated by fluvial, coastal or desert processes. Continental interiors at low latitudes, which in other eras might host rivers, lakes and wind-formed dunes, are swept by ice that grinds their surfaces and leaves behind deposits characteristic of cold climates. As a result, the rock record from this time includes glacially derived sediments and landforms in areas that correspond to ancient tropical and subtropical latitudes. The vertical dimension of the landscape also changes under the influence of long-lasting ice cover. The great thickness of the ice sheets causes the lithosphere to flex downward in the regions of greatest load. This depression can create basins that collect subglacial sediments and meltwater deposits. Around the edges of these basins, uplifted areas may experience enhanced erosion, as ice flows from higher ground into the depressed centres. Over millions of years, the combined effect of this flexure and the erosive power of ice can reduce the overall relief of mountain belts, lowering peaks and filling valleys. The roughness of the original landscape is diminished in many areas, replaced by smoother, gently undulating surfaces over which ice continues to move. Along some margins, subglacial meltwater, aided by the pressure of overlying ice carves long tunnel-like conduits within or beneath the ice sheets. When flow conditions allow, these conduits can carry large volumes of water charged with suspended sediment. As the water slows, sediments are deposited in the tunnels, forming sinuous ridges of sand and gravel known as eskers. In other settings, meltwater spreads out in broad sheets under or in front of the ice, laying down outwash plains of better sorted sands and gravels. These features remain aligned with ice flow and margin positions, and add to the suite of landforms that register the presence and behaviour of the ice. Dust also plays a role at the surface. Fine material generated by glacial grinding can be lifted by winds, especially from marginal areas, where ice-free patches or thinly ice-covered surfaces are exposed. This dust can travel long distances through the dry, cold atmosphere before settling. Where it accumulates on the ice, it can form darkened layers that on small scales slightly increase the absorption of sunlight, sometimes contributing to localized melting or alteration of the ice surface. Where it settles on exposed rock or sparse soil in nunatak regions, it can form thin covers that influence subsequent weathering. Through all of these processes, the ice acts as an agent that both erodes and deposits. It removes material from some places, carries it over great distances, and lays it down in others in patterns that reflect the geometry and dynamics of the ice sheets. The resulting arrangement of polished bedrock surfaces, striated pavements, moraines, tills, streamlined forms, and scattered stones on land and continental shelves forms a complex but coherent imprint of the snowball state on the solid surface of Earth. This imprint will persist long after the ice itself is gone, providing a durable record of how far and how deeply the ice once reshaped the continents and nearby shallow seas. Beneath the continuous shell of ice on a snowball Earth, the global ocean remains liquid over most of its depth, held above its freezing point by the combined effects of salt internal heat and pressure. Yet its character is very different from that of an open wind-stirred sea. The thick sea ice and snow at the surface act as an insulating lid that greatly reduces direct exchanges of heat momentum and gases between water and air. Without the constant churning by winds and waves, and without the regular seasonal formation and melting of sea ice across wide open margins, the structure and circulation of the ocean settle into patterns controlled more by slow density-driven flows than by rapid surface forcing. Near the underside of the ice, the uppermost layer of seawater is cold and close to its local freezing point. As sea ice forms from this water, it rejects part of its salt into the liquid that remains. This brine is colder and saltier than the surrounding water and therefore denser. It tends to sink sliding down through the upper ocean and spreading along pathways set by the underlying topography and existing density gradients. In the early stages of global glaciation, this process can help ventilate deeper layers by injecting dense surface waters downward. As sea ice advances and the area of new ice formation widens, large volumes of such dense brines are produced in low and mid-latitude regions that did not previously experience intense winter freezing. Over time, these descending plumes of salty cold water contribute to building a deep ocean that is both cold and stratified by salinity. With the surface sealed, wind-driven mixing is much weaker than in an open ocean. In normal conditions, winds blowing across the sea surface create currents and turbulence that stir the upper layers, bringing nutrient-rich deeper waters up and carrying oxygen-rich surface waters down. Under continuous ice cover, this input of momentum is muted. Any motion imparted to the ice by winds is largely taken up by deformation within the ice itself, such as ridging and rafting, rather than being transmitted directly into the water. The upper ocean therefore becomes more quiescent. Small-scale convection still occurs where brine is formed, and tidal motions and internal waves can propagate along density interfaces, but large storm-driven surface mixing is largely absent. The absence of strong surface forcing, combined with the stabilizing influence of salinity gradients created by brine rejection, encourages the development of a layered structure. At the top lies a very cold, relatively fresh layer that has interacted with melting ice and any limited inflow from continental margins. Below it, one or more layers of colder, saltier water settled during earlier phases of brine formation and sinking. At greater depths, particularly above the abyssal plains, water masses may reflect the balance between slow, downward diffusion of heat from the interior, small inputs from hydrothermal systems along mid-ocean ridges, and the long-term retention of any salinity contrasts established during the onset of global glaciation. Heat continues to rise from the interior of Earth through the ocean floor. Along mid-ocean ridges and at some volcanic seamounts, this heat is focused into hydrothermal systems. Cold seawater seeps into the crust, circulates through hot rock, and returns to the ocean through vents at temperatures far above the surrounding water. In a modern open ocean, hydrothermal plumes rise, mix and spread, delivering heat and dissolved minerals into the deep sea. During snowball conditions, these processes continue, but their influence is modulated by the altered background state. The cold, dense water filling much of the deep ocean limits the vertical extent of plumes, and the extremely stable stratification in some regions can confine them to particular layers. Over long timescales, however, the cumulative effect of hydrothermal and geothermal heat input is important because it helps prevent the deepest parts of the ocean from freezing, despite the strong cooling imposed from above. Ocean currents in this sealed world are driven mainly by differences in density and by the slow adjustments of water masses to sources and sinks of heat and salt. At high and mid-latitudes where thick ice rests over the ocean, and where sea ice once formed vigorously during the advance into the snowball state, dense waters may have sunk and spread along the seafloor, flowing along the slopes of continental margins and across deep basins. These currents, though slow, can transport large volumes of water over long distances, taking centuries to millennia to complete loops between formation regions and distant parts of the ocean. At lower latitudes, the presence of more illuminated ice above and slight differences in surface conditions may have allowed somewhat less dense waters to remain closer to the top, establishing a vertical gradient in density that resists further mixing. The usual pattern of wind-driven gyres, which in a warmer world carry warm water toward the poles at the surface and return cooler water toward the equator at depth, is largely absent. Instead, the circulation is dominated by thermohaline flows that seek to sort water masses according to their density. Tidal forces caused by the gravitational pull of the Moon and the Sun continue to act on the oceans beneath the ice. Tides raise and lower the ocean surface, flexing the ice cover and generating currents within the water. In regions where the ice is grounded or where its contact with the underlying water is constrained by seafloor topography, tidal motions can produce internal waves along density boundaries and induce local mixing. Over long timescales, tidal energy thus contributes to the redistribution of heat and salt, even in the absence of wind-driven turbulence. However, the overall level of mixing remains lower than in an open ocean, and the dense, cold state of the water column persists. The exchange of gases between ocean and atmosphere is severely restricted by the continuous ice cover. In a non-glaciated world, gases such as carbon dioxide and oxygen move between air and sea across the interface of open water. Wind waves and bubbles all facilitate this transfer. Under snowball conditions, the ice cover acts as a barrier. Only in rare leads, cracks or thin spots can gases directly cross between atmosphere and ocean, and these openings are small and intermittent. As a result, the ocean becomes more isolated as a chemical reservoir. The content of dissolved gases in the water is determined more by internal processes, such as biological activity and reactions with minerals, than by rapid exchange with the air above. This isolation has consequences for the distribution of substances such as oxygen, which affect how the deeper ocean evolves chemically and physically. But for now, the focus remains on the structural impact to reduced capacity for the ocean to quickly respond to changes in atmospheric composition. In spite of the rigid lid, the ocean beneath is not completely static. Over long spans of time, density contrasts tidal stirring geothermal heat input and the slow influence of any remaining buoyancy fluxes near continental margins, and fractures in the ice combine to maintain a subdued but persistent circulation. Water that becomes slightly warmer or fresher at some depth will tend to rise until it finds a level where its density matches that of its surroundings. Water that becomes cooler or saltier will sink. These gradual movements can create broad layered flows that gently slide past one another, transporting heat and dissolved materials. The timescales for these processes are long, often measured in thousands of years for full overturning cycles. In the context of a snowball Earth that may last tens of millions of years, however, such timescales are significant enough to allow the deep ocean to evolve and to maintain contact, albeit indirect and slowed, with the surface conditions that initiated the frozen state. At the boundaries between ocean and continent, where grounded ice sheets extend out over continental shelves, further complexity arises. Some portions of the ice may float as ice shells, with seawater flowing beneath. In these sub-ice shelf cavities, cold ocean water can melt the underside of the ice, where it's slightly warmer than the freezing point at that depth. The resulting fresher meltwater can rise along the base of the ice and escape at the ice front, altering local stratification. Conversely, in places where water in these cavities becomes supercooled, relative to the local freezing point, thin layers of ice can accrete onto the underside of the shelf, adding mass from below. The pattern of melting and freezing under ice shelves thus contributes to the exchange of heat and fresh water between the ocean and the overlying ice, even when the surface remains sealed from the atmosphere. Despite these local variations, the general picture of the Snowball Ocean is one of a cold, dense, and relatively still body of water capped by thick ice and decoupled from rapid atmospheric forcing. It continues to receive heat from the solid earth below and to adjust slowly through density-driven flows and tidal stirring. But it no longer participates in the rapid daily and seasonal exchanges that characterize an ice-free surface. Its circulation and structure reflect the conditions established during the onset of global glaciation and the constraints imposed by the persistent ice lid setting the stage for the chemical and biological processes that operate within this closed and muted marine environment. Within the oceans of a Snowball Earth, chemical and biological processes continue under conditions that differ strongly from those of an open sea. The thick ice cover limits direct gas exchange with the atmosphere, so the composition of seawater evolves mainly through internal reactions input from the seafloor and continental margins, and the activity of microorganisms that live in the dark or in the faint light that penetrates through ice. In the uppermost layer of the ocean, just beneath the base of the sea, ice water is very cold and close to its freezing point. Here, any light that filters through the ice can support a reduced but still present community of photosynthetic microbes. Where the ice is relatively thin, or where small leads and cracks form, sunlight penetrates into the water. Simple photosynthetic organisms use this light to fix carbon, taking up dissolved carbon dioxide and releasing oxygen. Their productivity is greatly diminished compared with that of an ice-free ocean, because the available light is weaker and more intermittent, but they nonetheless maintain some level of primary production in these marginal zones. The organic matter they produce serves as food for heterotrophic microbes that consume oxygen as they respire. A fraction of this organic matter sinks into deeper waters, carrying carbon and nutrients with it. The limited area of light access and the reduced overall production mean that the total flux of fresh organic material from the surface to depth is lower than in a warm open ocean, but over long time scales it remains an important driver of chemical change. Below the thin photic layer, the ocean is dark. Here the balance of chemical species is shaped by the consumption and transformation of the organic matter that descends from above and by dissolved substances supplied from the sea floor. As sinking particles are decomposed by microbes, they release nutrients such as nitrate and phosphate back into the water. They also consume dissolved oxygen in the process of respiration, because the ice cover restricts the replenishment of oxygen from the atmosphere, and because vertical mixing is weak in the strongly stratified water column, oxygen entering the deep ocean during the onset of glaciation can be gradually used up without being fully replaced. In many regions, especially at depth, oxygen concentrations may fall to low levels, or be exhausted, creating anoxic zones where no free oxygen is present in the water. In such environments, microbial communities switch to other electron acceptors for respiration, such as nitrate manganese oxides, iron oxides, and sulfate. When microbes reduce sulfate, they produce hydrogen sulfide, a dissolved gas that can accumulate in oxygen-poor waters. The presence of hydrogen sulfide and dissolved ferrous iron gives rise to a chemical state often described as sulfidic or ferruginous, depending on the relative abundance of these species. In different basins and depth zones, the balance between dissolved iron sulfate and other species can vary, and the vertical structure of the ocean may include layers with distinct redox conditions. Hydrothermal vents along mid-ocean ridges and volcanic arcs add another source of chemical diversity. Seawater circulating through hot crust dissolves metals and reduced compounds from the rocks. When this heated, chemically altered fluid emerges at vents, it mixes with surrounding cold seawater, precipitating some minerals and releasing others. These vents discharge fluids rich in substances such as hydrogen, sulfide, reduced iron, manganese, hydrogen, and methane. In the darkness of the deep ocean, these reduced compounds can serve as energy sources for chemoautotrophic microbes, which use chemical gradients rather than sunlight to drive carbon fixation. Dense microbial mats can develop around vent outlets, where temperature and chemical conditions are suitable. These communities populate a variety of microhabitats, including surfaces of vent structures, nearby sediments, and suspended particles within rising plumes. In the Neoproterozoic Snowball Ocean, such hydrothermal systems offer stable sources of energy and nutrients that are largely independent of surface conditions. chemoautotrophic microbes there can fix carbon dioxide into organic matter, supporting small local food webs even when surface photosynthesis is severely constrained by ice cover. Other microbes make use of the organic matter that settles from the surface photic zones or from vent communities themselves. Together, these chemotrophic and heterotrophic organisms link the deep ocean chemistry to both the seafloor and the limited light-influenced surface layer. Continental margins, though buried under grounded ice sheets and floating ice shelves, also influence the chemistry of the closed ocean. Where subglacial meltwater reaches the sea, it can carry dissolved ions and finely ground rock flour that have been produced by interactions between ice meltwater and underlying rocks. These inputs can supply nutrients such as iron, silica and phosphorus to coastal waters beneath ice shelves. In a sealed ocean, once introduced, such nutrients may circulate slowly along isopycnal surfaces over long timescales, because the density structure resists vertical mixing. Some of these substances may reach regions where light penetrates beneath thin ice, supporting limited photosynthetic activity. Others become part of the inventory of dissolved materials in deeper layers, where they participate in precipitation and dissolution reactions that slowly adjust mineral saturation states. The overall carbon inventory of the Snowball Ocean is shaped by several competing processes. Volcanic emissions supply carbon dioxide to the atmosphere, some of which dissolves into the surface ocean where contact remains. Photosynthetic microbes in accessible surface waters convert a portion of this dissolved inorganic carbon into organic matter, which can be respired back into carbon dioxide at depth or buried in sediments. Hydrothermal systems can add carbon in the form of dissolved inorganic carbon and reduced carbon species. The restricted gas exchange across the ice lid means that the return of carbon dioxide from the ocean to the atmosphere is limited, so over long intervals a disproportionate share of carbon may reside in the combined atmosphere-ocean system compared with warmer open ocean states. At the same time, the low temperatures and changing chemistry affect the form in which inorganic carbon is stored in seawater, shifting the balance among dissolved carbon dioxide bicarbonate and carbonate ions. In cold, dense and possibly high carbon dioxide waters, saturation states with respect to carbonate minerals can be different from those in later warm periods, influencing how and where carbonates can precipitate from solution or dissolve back into it. Nutrient cycles adjust to the unusual conditions of a sealed ocean. In a modern ventilated ocean, the upwelling of deep waters brings nutrients to the surface where they are used by phytoplankton while sinking. Particles export nutrients back to depth. Under Snowball conditions, the reduced vertical mixing and the presence of a stable stratification limit the upward flux of nutrients. As a result, nutrients required for photosynthesis may become depleted in the thin photic layer under the ice, further suppressing productivity. In the deep ocean, nutrients can accumulate as organic matter continues to be remineralized in the absence of regular removal to the surface. Over millions of years, this separation leads to a situation in which the deep ocean holds significant nutrient reservoirs, while the thin light-receiving surface layer remains relatively poor in some key elements. Microbial life adapts to this pattern by exploiting any local sources of nutrients. In regions near hydrothermal vents, bacteria and archaea use chemical energy to drive nitrogen and sulfur cycles, converting nitrogen between ammonium and nitrate and sulfur, between reduced and oxidized forms. In sub-ice shelf cavities and along continental margins, microbial communities in sediments and pore waters process organic matter delivered from above, releasing nutrients back into the overlying water, where they can occasionally be mixed upward by tides or small-scale convective events. In the water column, free-living microbes and those attached to particles conduct a wide range of transformations, including the oxidation of reduced metals and gases and the reduction of oxidized species when oxygen is scarce. These processes together maintain a complex web of chemical reactions that operates even in the absence of intense surface productivity. The physical isolation of the Snowball Ocean does not eliminate life. It reshapes the environments in which life persists. Microbes dominate these oceans, occupying niches defined by gradients in light temperature, redox state, and chemical composition. Near the base of the ice in low-latitude regions, where sunlight still penetrates thin layers of water, support photosynthetic communities adapted to very low light. Their pigments and cellular machinery are tuned to make use of the filtered spectrum that passes through snow and ice. In the dark interior of the ocean, chemotrophs exploit redox gradients near hydrothermal vents in sediments and along interfaces between oxygenated and anoxic waters. Heterotrophs consume organic matter wherever it collects, whether in particle-rich layers in sediments or in biofilms on mineral surfaces. Over time, the balance between these different microbial processes helps set the concentrations of dissolved substances such as sulfate ion methane and hydrogen sulfide, which in turn feed back on which metabolic strategies are most favourable in each region. In some zones, repeated microbial cycling can drive the system towards states where certain elements are predominantly in reduced form. In others, inputs of oxidants from limited exchange with the atmosphere or from photochemistry in near-surface waters maintain pockets of more oxidized conditions. Although the details of this chemistry vary from basin to basin and remain a subject of ongoing reconstruction and modelling, the broad outline is that of a stratified, chemically diverse ocean in which life continues in altered forms. The closed nature of the system slows the response of ocean chemistry to external changes, but it does not stop internal adjustments. Over spans of millions of years, the continued addition of volcanic gases to the atmosphere, the slow supply of heat from the interior, and the persistent work of microbial communities gradually shift the composition and structure of the ocean. These gradual changes prepare the system for later transitions in which the thick ice cover will thin, gas exchange with the atmosphere will strengthen, and the chemical inventories of both ocean and air will move toward new states that support different kinds of ecosystems. For the duration of the Snowball interval, however, the dominant picture remains that of a cold, layered and largely sealed ocean, where chemistry and life interact quietly, but persistently, beneath a continuous cover of ice. On the seafloor beneath the Snowball Earth, sediments continue to accumulate in patterns that quietly record the presence and behaviour of ice at the surface. In deep basins far from continents, fine particles settle through the cold, still water. Much of this material comes from the slow rain of tiny mineral grains and fragments of organic matter that descend from the upper ocean, even though surface productivity is low. Over thousands and millions of years, these particles form thin, uniform layers of mud that drape the underlying topography. Their composition reflects the chemistry of the sealed ocean, including the balance between iron, manganese, and sulfur in the water, and the limited but persistent input of dust from the atmosphere and minerals from hydrothermal vents. Closer to continental margins, where ice sheets and ice shelves interact with shallow seas, the sediments carry a more direct imprint of glacial processes. Under grounded ice that advances onto continental shelves, the bed is scoured and reshaped. As the ice moves, it entrains broken rock and older sediment at its base. Some of this debris is delivered to the edge of the grounding line, where it is released into the water as the ice begins to float. Large blocks may tumble directly into the sea and sink quickly, while finer material is washed out in plumes of sediment-laden meltwater. These processes create beds of poorly sorted sediment on the shelf, ranging from clay and silt to pebbles and boulders. Over time, this mixture can be reworked by currents that still flow, albeit weakly, beneath the ice shelves. But the overall character remains that of unsorted angular debris typical of glacial influence. In slightly deeper water beyond the grounded ice, large masses of ice, carved from the margins of ice shelves and outlet glaciers. These icebergs carry with them the debris they have gathered during their journey over land. As they drift and melt, they release their cargo. Each stone or boulder that falls from the ice descends through the water column and comes to rest on the seafloor. In many cases, it lands on fine-grained sediments that are accumulating slowly from the background rain of silt and clay. When such deposits eventually harden into rock, they contain scattered coarse fragments embedded within much finer material. These isolated clasts, later known as drop stones, deform the layers beneath them as they penetrate the soft sediment and are gradually buried. Their presence in what would otherwise be monotonous mudstones and siltstones is a distinctive marker of ice rafts that once passed overhead. Even where sea ice forms directly from freezing seawater, it can transport small particles. Dust that settles on the ice surface may be incorporated into the ice cover as it thickens. When pieces of this ice break off and drift, they can carry the dust with them. When they melt, the particles are released and add to the fine material accumulating on the seafloor. In some settings, sea ice may also pick up small stones from coastal areas where it grows around pebbles and cobbles on the shore or on shallow shelves. The later release of these stones into deeper water produces an additional, though modest, contribution to the dropstone population. On the continental slopes that mark the transition from shallow shelves to deeper basins, the buildup of glacially derived sediment can lead to episodes of instability. As layers of poorly consolidated muds, sands, and gravels accumulate under the edge of advancing and retreating ice, their weight and the shape of the slope may exceed the strength of the underlying materials. Portions of the sediment pile can fail and move downslope as turbidity currents dense flows of sediment-laden water that travel along the seafloor. These flows erode material from the slope and deposit graded beds in deeper basins with coarser grains settling first and finer grains following. In the context of Snowball Earth, such mass flow deposits may occur beneath thick ice, with no direct connection to a storm-driven surface, but their internal structures still record the dynamics of underwater slope failure and flow. In addition to these gravity-driven processes, quieter suspension settling continues in many basins. Fine particles derived from glacial grinding on land and from chemical precipitation in the ocean slowly accumulate. The presence of iron-rich waters in some parts of the ocean, shaped by limited oxygen and ongoing hydrothermal input, can lead to the intermittent formation of iron-rich layers. When conditions favour the precipitation of iron minerals from seawater, thin beds of iron oxide-rich sediment can form, sometimes alternating with layers dominated by silica or clay. These banded deposits, later recognised as iron formations in the rock record, point to a deep ocean that has cycled between different redox states during the long ice-covered interval. On land beneath the thick ice sheets, the tills and other glacial deposits that are forming underfoot will with time and burial become solid rock. As additional ice advances and retreats above them, they may be compacted and overlain by more sediment. When the ice eventually disappears and erosion exposes these layers, they will appear as diamictites rocks, composed of a wide range of class sizes set in a finer matrix. Some of these diamictites sit directly on older non-glacial sediments or on eroded bedrock surfaces, marking sharp transitions in the stratigraphic record. In some regions, they display features such as striated clasts, faceted stones, and deformational structures that reflect the direct action of ice. In other areas, they show signs of deposition from debris-laden meltwater flows with imbricated clasts and crude layering. The distribution of these glacial sediments on the ancient seafloor and on continental surfaces is not limited to high paleolatitudes. Because the continents during the Neoproterozoic are arranged in low and mid-latitude positions, many of the deposits being laid down under and around the ice sheets are forming near the equator. The magnetic minerals within these sediments and associated volcanic rocks align with Earth's magnetic field at the time of their formation. As the rocks lithify, this alignment becomes locked in. In future analysis, this remanent magnetization will allow the original latitude of deposition to be estimated by measuring the inclination of the preserved magnetic signal. In the present context, these sediments are simply accumulating in places that, in terms of planetary geometry, receive strong sunlight, but are nonetheless buried under ice. In shallow epicontinental seas that lie over flooded portions of continents, the sedimentary record reflects alternating phases of direct glacial influence and quieter background deposition. When grounded ice extends into these basins, till and other subglacial deposits form at the bed. When the ice margin retreats slightly, marine waters flood the area under an overlying cover of floating ice. Fine sediments settle from suspension, and occasional dropstones fall from drifting ice blocks. Repeated shifts in ice position can build up sequences in which coarse unsorted layers alternate with finer, more uniform mudstones. Within these successions, features such as deformed laminae, soft sediment folds, and clastic dikes indicate episodes where the weight and movement of ice have disturbed partially consolidated sediments. As sediments accumulate and compact under their own weight, the water they contain is squeezed out. Pore waters migrate along permeable layers and through fractures interacting with mineral grains and altering some of them. Clay minerals may transform into more stable forms under burial, and carbonate cement can precipitate from solutions strengthening the rock. The original textures of glacially derived sediments are partly preserved, but also modified by these diagenetic processes. Nonetheless, key indicators such as the wide range of class sizes, the lack of sorting, and the presence of faceted and striated stones remain recognizable. In some sections interbedded with the glacial sediments, there may be layers of volcanic ash. These derive from eruptions that send fine particles high into the atmosphere, some of which eventually fall onto the ice surface or directly into open or ice-covered waters. When ash layers settle through water and accumulate on the seafloor, they can later be altered to clays or other minerals, but they often retain a distinct composition. These layers provide time markers that tie the glacial sedimentary record to volcanic events and through radiometric dating to absolute ages. Over the long duration of Snowball Earth, the combined effect of all these processes is the creation of a stratigraphic archive that encodes information about ice cover sediment transport, ocean chemistry, and volcanic activity. On continental margins, thick wedges of glacial marine sediments build out over the shelves and slopes. In deep basins, blankets of fine mud punctuated by dropstones and occasional gravity flow deposits cover large areas. On land, diamictites and related glacial rocks overlie older non-glacial strata and underlie later deposits that will form after deglaciation. Within these rocks, the physical features of clasts and bedding, the chemical signatures preserved in minerals and isotopes, and the magnetic properties locked into iron-bearing grains together form a record of Snowball Earth that will persist long after the ice vanishes. For now, these sediments are simply layers accumulating grain by grain, pebble by pebble on the seafloor and beneath the ice, quietly registering the conditions of a frozen planet. In the stratigraphic record that forms during and after Snowball Earth, the glacial sediments and scoured surfaces created under ice are only part of the story. Above many of these diamictites and dropstone-bearing mudstones lies another kind of rock that stands out by its sharp contact and distinctive character. This rock is a relatively pure carbonate, often forming thick, laterally extensive beds that blanket the underlying glacial deposits. Because it caps the glacial sequence, it is commonly referred to as a cap carbonate. Its presence, geometry, and internal features quietly record a profound change in the state of the planet. On many ancient continental margins, the contact between glacial sediments and overlying cap carbonates is abrupt. At the base of the carbonate unit, pebbles and larger clays from the glacial deposits may be partially enclosed by the first carbonate layers, showing that sedimentation changed from ice-influenced debris flows and tills to chemically precipitated or biologically mediated carbonate deposition without a long intervening erosional episode. The lower part of the cap carbonate may contain brecciated zones, where fragments of the underlying glacial rocks are embedded in a carbonate matrix indicating early cementation and fracturing. Above this basal interval, the carbonate often becomes more uniform, forming centimetre to metre scale beds of limestone or dolostone that can extend over great distances. The surfaces of these beds carry evidence of the environment in which they formed. Some display delicate ripple marks produced by waves and currents in shallow water that moved over soft carbonate mud. Others show small-scale cross-bedding where inclined layers reflect the migration of low sand or silt-sized carbonate dunes on the seafloor. In places, polygonal crack patterns cut through the upper surfaces of beds and are filled with later sediment indicating episodes of exposure and shrinkage of cohesive carbonate muds. In some regions, large gently undulating structures on bed tops, sometimes interpreted as large wave-formed ripples, point to vigorous water motion in the shallow seas that spread across continental shelves soon after deglaciation. The origin of these cap carbonates is closely tied to the chemical state of the ocean and atmosphere at the end of the snowball interval. During the long period of global ice cover, volcanic activity continues to release carbon dioxide into the atmosphere. Because chemical weathering of exposed rock surfaces is greatly reduced beneath the ice, this carbon dioxide is removed from the atmosphere and ocean far less efficiently than in a warm world with active rainfall and rivers. Over millions of years, the concentration of carbon dioxide in the combined atmosphere and surface ocean can build up to levels much higher than before the glaciation. When deglaciation begins driven by this strong greenhouse forcing and by the accumulation of heat in the system, the retreat of ice exposes fresh rock surfaces across large areas of the continents. The newly uncovered rocks have been scoured clean by glaciers, leaving unweathered minerals in direct contact with the air and the first meltwaters. In the warmer, wetter conditions that follow the collapse of the ice sheets, chemical weathering on land accelerates. Rainwater rich in carbon dioxide reacts with silicate and carbonate minerals, generating dissolved calcium, magnesium, bicarbonate, and other ions that rivers carry to the sea. At the same time, the warm surface oceans, now receiving more direct sunlight and in contact with a carbon dioxide-rich atmosphere, become oversaturated with respect to carbonate minerals. Oversaturation means that seawater contains more dissolved inorganic carbon and calcium than would be in equilibrium with existing carbonate solids under the prevailing temperature and pressure. Under such conditions, carbonate minerals can precipitate rapidly, either directly from seawater or assisted by microbial activity that modifies local chemistry. The combination of high weathering input from land-elevated atmospheric carbon dioxide and warm, relatively calm shallow seas over flooded continental shelves provides conditions favourable for widespread rapid formation of carbonate sediments. Cap carbonates thus accumulate quickly in geological terms, laying down thick layers of chemically derived rock in a relatively short interval following ice retreat. Their limestones and dollostones often show internal fabrics that hint at rapid precipitation. Some contain laminated, finely crystalline textures that suggest early cementation from supersaturated waters. Others display unusual structures such as steeply inclined sheet, like veins of carbonate that cut through the sediment and may have formed through disruption and injection of semi-consolidated mud while cement was forming. In some cap carbonate sequences, seafloor cements grow as crystal fans that radiate upward from bedding planes, forming distinctive textures. These crystal fans can be composed of calcite or dolomite and suggest growth into open water from the sediment surface, again pointing to strong supersaturation. The chemistry preserved in cap carbonates carries further information about the transition from a frozen planet to a warm one. When carbonate minerals form, they incorporate carbon from dissolved inorganic carbon in seawater, and the ratio of the heavy to light isotopes of carbon in these minerals reflects the isotopic composition of the oceanic carbon pool at the time of deposition. Many cap carbonates show unusually low ratios of heavy to light carbon, compared with typical marine carbonates. This pattern indicates that before and during their formation, the oceans held a large amount of isotopically light carbon, likely derived from the oxidation of organic matter that had accumulated during the snowball interval, or from other reservoirs of reduced carbon. The sudden shift to these low ratios at the base of cap carbonates, followed by gradual returns toward more typical values, up section suggests a rapid reorganization of carbon reservoirs as the climate warmed, the ice melted, and circulation and gas exchange between ocean and atmosphere strengthened. Other isotopic systems in cap carbonates and associated rocks, such as those involving strontium and oxygen, provide additional clues. The ratio of different strontium isotopes in marine carbonates depends on the balance of inputs from continental weathering and from hydrothermal activity at mid-ocean ridges. High values of the radiogenic isotope in some cap carbonates point to enhanced weathering of continental crust during deglaciation, consistent with the increased runoff from newly exposed, rapidly eroding land surfaces. Oxygen isotopes in carbonate can be influenced by temperature and the isotopic composition of seawater. While interpretations are complex, some data suggest that surface waters during cap carbonate formation were relatively warm, supporting the idea of strong greenhouse conditions immediately after Snowball Earth. Cap carbonate successions are not uniform from one region to another. In some areas, the carbonate layer is only a few meters thick. In others, it reaches tens of meters. The specific mineralogy varies, with some dominated by limestone and others by dolostone. Local variations in water depth, distance from shore, and underlying topography influence sediment textures and structures. Yet despite these differences, the broad pattern of a distinctive carbonate unit directly overlying glacial deposits, often of similar age across widely separated continents, stands out as a recurring feature. When combined with paleomagnetic data from these rocks, and from underlying glacial units which indicate formation at low paleolatitudes, in many cases this pattern supports the reconstruction of a planet that experienced near global ice cover, followed by abrupt and intense deglaciation. Above the main body of cap carbonate, the sedimentary record transitions into more typical marine sequences. Mudstones, siltstones, and fine sandstones resume their roles as the dominant clastic sediments on continental shelves and slopes. Carbonate deposition continues in some settings, but now as part of more ordinary shelf and platform systems, influenced by waves, tides, and biological activity in a world with open oceans and active weathering. The cap carbonate stands at the base of these post-glacial successions as a marker of a short interval during which ocean chemistry and climate were far from ordinary. On land, where erosion has cut deeply into the crust sequences of Neoproterozoic rocks, display this pattern of glacial diamictites, dropstone-bearing marine mudstones and overlying cap carbonates in many regions, including parts of present-day Australia, North America, Africa, and China. In mountain belts where tectonic forces have folded and uplifted these rocks, they now appear as tilted layers and cliffs. Geologists examining them piece together the order of events. First, the advance of ice, and the deposition of glacial sediments. Then the sudden switch to carbonate precipitation in newly warmed flooded seas. And finally, the return to more conventional sedimentation. The cap carbonates thus serve as a geological signal of thaw, a record in stone of the time when the thick ice cover melted back, continental runoff surged, and the oceans underwent a rapid shift in chemistry as the Earth system moved from a stable extreme glacial state toward a more temperate configuration. In a purely physical sense, they capture the moment when the balance between incoming energy greenhouse gases and reflective surfaces tipped in the opposite direction from that which had locked the planet into global ice. In the stratigraphic column, they form a clear boundary between the deposits of a frozen world and those of the warmer, more dynamic oceans that follow. In the microscale environments that persist within and beneath the ice of a Snowball Earth life continues in forms that are simple, yet remarkably resilient. Even while the planetary surface appears from a distance to be locked in uniform, white close inspection of the ice water and rock reveals many small refuges where liquid water, dissolved nutrients and energy sources come together in ways that allow microorganisms to survive. Within the thick sea ice that covers the oceans, salt is rejected as crystals grow, creating complex networks of tiny channels filled with very cold, salty brine. These brine channels thread through the ice like narrow corridors. In them, water does not freeze because its salinity depresses the freezing point, and despite the low temperature it remains liquid. Dissolved nutrients from the underlying ocean enter these channels, and faint light filtered through meters of ice and snow penetrates from above, especially at low latitudes where the sun stands higher in the sky. Photosynthetic microbes adapted to dim blue shifted light occupy the walls and pools of these channels. Their cells attach to ice surfaces or float in the brine, carrying pigments that capture the scarce photons available. They fix carbon from dissolved carbon dioxide and release oxygen, operating slowly but persistently during periods when light is present. In deeper parts of the ice and at higher latitudes where light is extremely weak or absent, for long intervals microbes rely less on photosynthesis and more on chemical energy stored in organic matter or on redox gradients between oxidized and reduced compounds in the brines. In some regions, wind-blown dust and fine rock particles accumulate on the ice surface. Darker than the surrounding snow, these particles absorb sunlight, causing slight local warming and shallow melting. Small depressions filled with meltwater can form around such aggregates, creating water-filled pockets that host microbial communities. Within these microbasins, often referred to in modern analogues as cryoconite holes, microbes bind mineral grains together with sticky substances forming dark granules that settle to the base of the melt pocket. There they experience cycles of freezing and thawing, periods of light and darkness, and fluctuating concentrations of nutrients and gases. These variable conditions select for organisms that can tolerate repeated stress, survive desiccation when water refreezes, and resume metabolic activity when liquid returns. Under the great continental ice sheets, other refuges exist where liquid water persists, despite the overall cold. Geothermal heat from Earth's interior, combined with the insulating effect of thick ice, can bring temperatures at the base of the ice sheet to the melting point. In such regions, basal meltwater collects in thin films, small ponds, or larger subglacial lakes that are completely cut off from direct contact with the atmosphere. These waters draw their chemical character from interactions with the underlying rocks and sediments. As meltwater flows along the base, it leaches minerals from crushed and ground rock flour, becoming enriched in ions, such as calcium, magnesium, iron, and silica. Microbial communities in these subglacial waters exploit the chemical gradients created by rock-water reactions. Some microbes oxidize reduced iron or sulfur compounds using the released energy to fix carbon. Others reduce oxidized species such as nitrate or sulfate, closing local redox cycles. Organic matter reaching these environments from overlying ice or from older sediments provides an additional energy and carbon source. Although isolated, these ecosystems remain active on timescales of years to centuries, supported by the steady, modest supply of heat from below and slow meltwater fluxes. Where subglacial meltwater finds paths to the ocean, it may flow through tunnels beneath the ice, joining networks of channels that carry cold sediment-rich water toward grounding lines and sub-ice shelf cavities. In the walls and beds of these tunnels, biofilms form on mineral surfaces. Microbes coat grains of sand pebbles and larger clasts with thin, slimy layers, anchoring themselves where flow conditions deliver a steady though sparse supply of nutrients. In some places, mineral deposits precipitate from the water as it changes temperature and pressure trapping cells and their metabolic products within growing crusts. These microbially influenced mineral coatings contribute to the subtle texturing of subglacial sediments and may later serve as sites of distinctive chemical signatures. In deeper oceanic settings, hydrothermal vents at mid-ocean ridges and volcanic centres remain important microhabitats. The seawater that is circulated through hot crust emerges as warm or hot fluid, laden with dissolved minerals and reduced chemicals. Around vent orifices, steep gradients in temperature and composition arise over distances of centimetres to metres. Microbial mats colonise these gradients, positioning themselves where conditions are favourable. Close to the vent, heat-tolerant organisms extract energy by oxidising hydrogen, sulfide hydrogen, methane, or ferrous iron, using that energy to fix carbon into organic matter. Slightly farther away, where vent fluids have mixed with cold ambient seawater, other microbes take advantage of intermediate conditions. The result is a patchwork of small-scale niches, each defined by particular combinations of temperature, pH, and chemical composition. On the surfaces of vent chimneys, in cracks in the surrounding basalt, and within nearby sediments, microbial communities persist, sheltered from the extremes of the global surface climate by the constant input of geothermal energy. Microscale refuges are not limited to ice and submarine vents. Within rocks themselves, pores and fractures filled with thin films of water can host endolithic communities, microbes that live inside mineral matrices. In areas where volcanic activity brings warm rock close to the base of the ice, circulating fluids pick up heat and dissolve ions from new igneous material. Microorganisms occupy microfractures in these rocks, using chemical gradients between rock surfaces flowing water and trapped pockets of gas to drive metabolism. Even in colder, more stable crustal settings, some microbes live at depths where temperature and pressure keep water liquid, and where slow diffusion supplies the compounds they need. These deep biosphere communities operate at extremely low metabolic rates, with individual cells dividing only rarely, yet over geological times they contribute to the persistence of life. Near the bases and margins of ice sheets, where pressure and geothermal heat combine with occasional frictional heating from ice flow, thin zones may experience brief or localized melting. In such zones, small cavities and crevasses partly filled with water can open and close. Microbes can be transported into these spaces by flowing meltwater or by being carried within the ice itself. When water refreezes, some cells become trapped within the ice matrix but remain viable, able to resume activity when conditions permit. Others survive in unfrozen films along grain boundaries. The capacity of microbial cells to withstand freezing, drying, and high salt concentrations, aided by protective molecules and robust cell walls, allows them to persist through cycles that would be lethal to many larger, more complex organisms. In shallow marine regions beneath thinner ice, or near low-latitude margins of the sea, ice cover slightly higher. Fluxes of light and nutrients may allow more continuous photosynthetic activity in the water column just below the ice. Here, filamentous cyanobacteria and other photosynthetic microbes form delicate mats on the underside of the ice, hanging into the water like dense carpets. These mats trap particles and enhance local nutrient retention. As they grow and slough off fragments, they produce small aggregates that sink, slowly feeding heterotrophic microbes in the water below. In this way, even thin belts of relatively active photosynthesis can support small vertical food chains in an otherwise low-productivity ocean. The persistence of these microhabitats over long durations depends on the stability of the physical conditions that sustain them. Geothermal heat flow is steady on human and even on many geological timescales, maintaining liquid water in some subglacial and deep rock environments regardless of the state of the surface. Hydrothermal activity may fluctuate as volcanic systems wax and wane, but mid-ocean ridges and many submarine volcanic centers remain active across the Snowball interval. Ice dynamics continue to generate brine channels, cryoconite-like features, and melt pockets as long as ice exists. As a result, while the global environment is hostile to large complex organisms and to extensive surface ecosystems, a mosaic of small refuges remains available where microorganisms can endure. These communities are sparse compared with the rich ecosystems of later warm periods, and their metabolic rates are often low, but they maintain genetic and metabolic diversity. Over millions of years, mutations and selection in these isolated pockets explore variations in biochemical pathways, membrane structures, and strategies for coping with stress. The products of this slow evolution are not obvious at the scale of the planet during the Snowball state. They are visible only in the composition of microbial assemblages occupying tiny niches in ice water and rock. Yet they ensure that when external conditions begin to shift, there are surviving lineages with the capacity to respond, expand, and interact with newly available environments. For the duration of global glaciation, life remains mostly confined to these hidden microenvironments, continuing quietly in the thin boundaries between solid and liquid, between rock and water, and between complete freezing and the narrow persistence of fluid habitats. As carbon dioxide from millions of years of volcanic activity accumulates in the atmosphere over a Snowball Earth, the greenhouse effect slowly strengthens above the bright ice-covered surface. For much of the glacial interval, the high albedo and low water vapor content of the atmosphere keep the planet cold despite this buildup. Over long spans of time, however, the continued addition of greenhouse gases shifts the balance between incoming sunlight and outgoing infrared radiation. At some point, the combined warming effect of elevated carbon dioxide geothermal heat, input from below, and the slow redistribution of heat within the ocean and crust brings parts of the system to a threshold. Regions beneath the ice that are most sensitive to warming, such as low-latitude areas, receiving strong sunlight and zones above relatively warm ocean waters, begin to experience increased basal melting. The ice cover, once nearly stable on geological timescales, becomes thinner in some belts and more mobile. Cracks and leads open more frequently in the sea ice, exposing dark water to the sun. These openings absorb more solar energy than the surrounding ice and accelerate local warming. As summer seasons lengthen and strengthen under a greenhouse-rich sky, meltwater ponds and channels expand across the surfaces of ice sheets and sea ice in low and mid-latitudes. Meltwater on top of ice can drain downward through fractures, lubricating parts of the ice sheets and promoting faster flow toward their margins. In coastal regions, ice shelves thin from above and below as warmer ocean waters circulate beneath and warmer air passes overhead. Calving rates increase, sending more icebergs into the ocean. As the mass balance of the ice sheets becomes negative over large areas, their grounding lines retreat, and continental ice cover begins to shrink. The loss of ice and snow surfaces reduces planetary albedo, allowing more sunlight to be absorbed by exposed land and open water. This shift enhances the warming trend in a feedback opposite to the one that once drove the planet into global glaciation. Deglaciation proceeds in stages. At first, low-latitude oceans gain seasonal or permanent openings in the ice cover. Surface waters there now in direct contact with the atmosphere can exchange gases rapidly. Dissolved carbon dioxide builds up to high levels in the upper ocean as the atmosphere enriched during the Snowball interval equilibrates with the sea. In some models and hypotheses, additional oxidants such as hydrogen peroxide produced by ultraviolet radiation acting on ice and snow during the glacial period are stored in the ice and released upon melting. When combined with increased photosynthesis in newly sunlit waters, such inputs may contribute to pulses of oxygenation in the atmosphere and surface ocean. These details remain under study, but it is widely held that the end of Snowball Earth coincides with significant changes in oxygen levels and redox conditions. On land, the retreat of ice sheets exposes large areas of freshly abraded bedrock. Glacial erosion has removed pre-existing soil and weathered rock leaving surfaces rich in minerals that are reactive with water and carbon dioxide. As temperatures rise and precipitation increases in the new greenhouse climate, intense chemical weathering begins. Rainwater acidified by dissolved carbon dioxide attacks silicate and carbonate minerals, generating rivers charged with calcium, magnesium, bicarbonate, and other ions. These rivers deliver large fluxes of solutes and suspended glacial flour to the coastal oceans. The influx of nutrients such as phosphorus, iron, and silica stimulates primary productivity in surface waters. Photosynthetic microbes, including cyanobacteria and early eukaryotic algae, spread rapidly in the newly opened seas, especially in low-latitude regions, where sunlight is abundant. Their activity draws down part of the elevated carbon dioxide in the surface ocean and releases oxygen, contributing to the evolving composition of the atmosphere. At the same time, the high bicarbonate and calcium concentrations in seawater, combined with warm temperatures, favour extensive precipitation of carbonate minerals, producing the cap carbonate layers that settle over glacial sediments on continental shelves and slopes. The oceans, once stratified and sealed, begin to overturn more vigorously as winds re-establish their influence on the surface and as temperature and salinity gradients adjust to the new climate. Deep water that has accumulated reduced species such as ferrous iron and possibly hydrogen sulfide during the snowball interval mixes with oxygenated surface waters. This mixing leads to widespread oxidation of reduced compounds and changes in the chemistry of the deep sea. Iron that was once dissolved precipitates as iron oxides and sulfur cycles adjust, as sulfate becomes more abundant and hydrogen sulfide is oxidized. These shifts are recorded in the mineralogy and isotopic composition of sediments deposited during and after deglaciation. The increase in oxygen and the reorganization of redox conditions create new opportunities and challenges for microbial life. Organisms that can tolerate and exploit higher oxygen levels, including those with pathways for efficient aerobic respiration, gain advantages in many environments. Others retreat to niches where noxic conditions persist, such as restricted basins, sediments, and parts of the subsurface. The overall structure of microbial ecosystems changes as oxygen penetrates deeper into the water column and sediments than before. In the newly warmed oxygenated surface ocean, eukaryotic plankton diversify. Single-celled organisms with internal structures, and in some cases mineralized walls or skeletons, occupy a variety of ecological roles. Some act as primary producers, others as grazers of bacteria and smaller cells. Their interactions build more complex food webs than those dominated solely by prokaryotes. In shallow marine environments along continental margins, microbial mats colonize sand and mud surfaces, stabilizing sediments and creating layered communities. Within and above these mats, early multicellular organisms appear. The fossil record from the interval after the last major Neoproterozoic glaciations shows the first abundant macroscopic soft-bodied organisms commonly grouped into what is now called the Ediacaran biota. These organisms display a range of forms. Some are frond-like structures anchored to the seafloor, with quilted or segmented appearances. Others are more disc-shaped or elongated, lying flat on or within microbial mats. Many lack obvious hard parts or clear modern analogues, and their exact biological affinities remain uncertain. What they share is a multicellular organisation with differentiated tissues or repeated modules that distinguish them from single-celled microbes and simple colonies. Their presence in sediments above cap carbonates and other postglacial deposits indicates that within tens of millions of years after Snowball Earth conditions and large and structurally complex organisms have become established in shallow marine ecosystems. Alongside these, body fossils trace, fossils begin to appear that record the activities of moving organisms. Simple horizontal burrows, small tubes penetrating sediment and surface trails suggest that some organisms are now capable of locomotion feeding at or just below the sediment-water interface. These traces mark a step toward more active interactions between organisms and their environments, including the mixing of sediments and more dynamic use of resources in space and time. In parallel, microscopic fossils from slightly earlier and overlapping intervals preserve clusters of cells and possible animal embryos, indicating that the genetic and developmental toolkit for building multicellular bodies is emerging and diversifying during and after the snowball times. On land, the immediate post-glacial world remains largely barren of large organisms. Weathering erosion and sediment transport reshape landscapes freshly freed from ice. Rivers carve new channels, deltas build out into rising seas, and coastal plains adjust to changing relative sea levels. Microbial communities, including biofilms and thin crusts, gradually colonize rock surfaces and soils, influencing the early stages of soil formation and chemical exchange between lithosphere and atmosphere. Over much longer timescales, plants and animals will eventually colonize terrestrial environments, but during the interval directly following Snowball Earth, the most dynamic evolutionary developments occur in the oceans. The link between global glaciations and the rise of complex life is still an area of active research. It is likely that multiple factors contribute, including the stress and selection imposed by extreme conditions, the reorganization of nutrient and carbon cycles during deglaciation, and the long-term increase in oxygen levels. What can be stated from the rock and fossil record is that major Neoproterozoic glaciations are closely followed in geological terms by the first widespread appearance of macroscopic multicellular organisms and by increasing complexity in marine ecosystems. The climatic recovery from a frozen state to a warm, high carbon dioxide world sets in motion changes that reverberate through the atmosphere, oceans, and biosphere. As time moves forward into the later Neoproterozoic and early Paleozoic, these evolving ecosystems will give rise to the first animals, with mineralized skeletons, the diversification of body plans during the Cambrian, and the gradual expansion of life into new environments. In this way, the micro-scale survival strategies of microorganisms during Snowball Earth, coupled with the large-scale physical processes that end global glaciation, lead into an era when life not only endures but expands in complexity, filling the newly available ecological space of a warmer, oxygen, richer planet. Thank you for watching and for spending this time with us. We look forward to seeing you again in the next episode where another gentle journey through science awaits.